Hello and welcome to Sleepy Science. Tonight we'll drift across the strange shoreline where causes blur and choices echo backward, where paths exist until you look and then politely fall into one. We'll pass a quiet switch that makes before and after trade places, peek into two labs that disagree about the very same moment, and listen as a theory argues with itself in a soft, logical whisper. You'll watch information vanish and then return like tide foam. See properties stroll away from their objects and open three boxes that insist the particle is both here and not here, with equal grace. We'll let entanglement link distant corners without sending a single message, test fairness until numbers break old promises, and feel time settle into crystals that tick without moving. Along the way, we'll weigh demons with thermodynamic bills, hold motion still, or speed it up by watching, and try on stories where freedom is only a carefully hidden assumption. We'll ask what a quantum state really is, a belief, a guide, or something undeniably real, and we'll learn to read between outcomes with tools gentle enough not to wake the system. If you listen closely, you'll hear the grammar that actions obey and the soft rule that not every question can be asked at once. Tell me where you're watching from, your city, your country, and what time it is there. And if these unhurried explorations help you rest, please like, subscribe, and share, so other sleepy minds can find their way here. Now take a long breath, let your shoulders drop, and join me at the quiet edge where curiosity glows. Probabilities hold their shape, and the night teaches gently. Delayed choice. Deciding. Yesterday, today. You trust the past because it feels sealed, like a book already printed. Yet the delayed choice experiment asks you to make a decision after the crucial page has supposedly turned and still watch the story settle differently. And that tiny twist, choosing your measurement after a photon has passed the place where you imagined its decision was already made, becomes your invitation into how quantum reality actually works. Begin with the cleanest version. A single photon enters an interferometer. Think of a simple light splitter that sends it along two possible paths. And much later, two detectors wait to record what arrives. If you leave the second beam splitter in place, the two paths are recombined, and the photon behaves in a way that yields an interference pattern in the statistics, which is what you expect if the two paths remain indistinguishable all the way to the end. If you remove that second beam splitter, the paths do not recombine. Each detector now corresponds to a distinct route, and the which path information becomes, in principle, available, so the interference disappears from the statistics. Delayed choice is nothing more and nothing less than making that recombination decision after the photon has already passed the first splitter and committed, in your classical imagination, to a route. You use a fast modulator or a rapidly insertable element so the apparatus can decide late. Do we recombine the paths or not? And the astonishing but repeatable result is that the subensemble of trials in which you did recombine shows interference, while the subensemble in which you did not shows no interference, even though your choice came too late by everyday logic. This is the point where your intuition wants to accuse the universe of retroactive editing. Did my current decision reach back and change what the photon did? But the experiment is teaching you a quieter, truer lesson. In quantum physics, the outcomes you can consistently talk about are defined by the entire measurement context, not by a picture of tiny pellets carrying pre-written histories through the device. The photon was not secretly following a definite path you simply failed to look at. Before detection, what existed was a superposition of alternatives whose ability to interfere depended on whether the final arrangement preserved or destroyed their indistinguishability. When the two paths remain indistinguishable, their probability, amplitudes add and you see interference in the long run counts. When the setup encodes which path information, even just in principle, even if you choose not to read it, the alternatives can no longer interfere and the counts settle into a non-interfering pattern. The timing matters only to your expectations, to the formalism and to nature's bookkeeping. What matters is the whole chain of what can, in principle, be known about the alternatives at the moment of detection. Notice what isn't happening. There is no usable signal sent to the past, no way to alter a recorded outcome after the fact, no violation of relativity or common sense about cause and effect that would let you send a message to yesterday. Each run produces a single click now, and the pattern emerges only after many runs are grouped according to the late choice you made. You're not rewriting an earlier measurement, you're finishing a measurement whose meaning depends on whether you allowed the paths to remain mutually anonymous. That phrase, mutually anonymous, does most of the conceptual work. Keep the alternatives anonymous and they can interfere. Tag them, even subtly, and the interference dissolves. This is complementarity expressed in hardware, not poetry. It's why the experiment is designed so the two options, recombine for interference or separate for which path, are mutually exclusive. You cannot have both at once because the conditions that let you tell paths apart are exactly those that destroy the delicate phase relations required to produce fringes. The delayed aspect simply forces you to drop the comfortable story that the photon's true nature was decided earlier and merely revealed later. Instead, you learn to speak in terms of what your complete arrangement allows you to infer, without contradiction. If you want a mental picture that doesn't mislead you, keep it procedural. First splitter prepares a superposition of path alternatives. The apparatus between splitters may add phases or tags. The second stage either erases the telltale differences and recombines the alternatives or keeps them separate. The detector statistics reflect the compatibility of those alternatives at the end. In practice, researchers ensure the late part by using high-speed electro-optic elements or random choices made fast enough that the photon cannot know the future configuration by any ordinary influence. The results match quantum predictions perfectly and never enable paradoxical communication. What about the temptation to say, the future decides the past? Some interpretations lean into that phrasing to emphasize time symmetry, but you don't need to recruit mystery to get the right answers. It's enough to accept that a path story you might tell about the photon must be consistent with the information, content of the entire experiment. And when you change what information is, in principle, available at the end, you change which story is admissible, not the earlier reality of a hidden marble choosing left or right. If you want to test your understanding, imagine a control dial labeled distinguishability from 0 to 1. At 0, paths are perfectly indistinguishable, and interference is maximal. At 1, paths are perfectly distinguishable, and interference is gone. Between them, you get partial fringes, exactly as experiments see when they introduce gentle tagging and then adjust it. That dial reminds you that what matters is not your decision's timestamp on a wall clock, but whether the quantum alternatives remain coherent through to the point of detection. The deeper human question, the one you secretly carry into the lab, is whether this means your present choices can redeem or rewrite your past. Physics will not give you that wish, yet it does nudge you toward a humbler insight. The meaning you attach to earlier events is not independent of the questions you are able to ask now. In the apparatus, your late choice does not travel backward. It closes a context, so the data can cohere. In a life, your current perspective does not change what happened, but it can determine which narrative survives. The one that splits your experience into separate paths with blame and certainty, or the one that lets patterns reappear when you stop insisting on labels. Either way, the lesson is the same. Reality at the finest scales is participatory, not because you bend the past, but because what counts as a sensible account of events depends on the web of relations you finally allow to meet at the point where you look. And that is enough to make you gentler with the stories you tell about photons and about yourself. Quantum eraser. Unknowing restores the impossible. You've felt what it's like to learn something that breaks the magic, like discovering a magician's secret and never being able to see wonder the same way again. And the quantum eraser is the rare experiment that shows you how to give wonder back, not by faking it, but by carefully choosing to make certain knowledge impossible so nature can do what looked forbidden a moment earlier. And your role in this story is not to tamper with the past, but to curate what the present can, even in principle, find out. Picture a single particle of light born as twins. One heads toward a screen, the other takes a different route to a flexible analyzer you control. At the start, the twins are entangled, which means neither is a complete story by itself, and the details that distinguish the signal's two possible paths are quietly recorded in joint correlations with the idler rather than written as a label. The signal carries alone. If you set your analyzer so the idler can reveal which path the signal could have taken, then the statistics you later sort by that choice refuse to show interference. Because path alternatives that are distinguishable, even just in principle, cannot combine into a single delicate pattern. But if you reconfigure the analyzer so those path clues are scrambled into overlapping possibilities so thoroughly that no measurement can retrieve them, then, when you collect only the signal detections that pair with this erased idler outcome, an interference pattern reappears inside that carefully selected subset, as if the world were saying, remove the distinguishing marks, and the wave-like cooperation between alternatives can breathe again. This is the essential logic of the quantum eraser in plain terms. Information about which way and the ability to display interference are mutually exclusive properties of the whole measurement arrangement. You don't restore fringes by pressing an undo button on history, you restore them by designing things so the which way record never crystallizes into anything that could, even in principle, be read. The most mind-stretching version adds a further twist of timing called the delayed choice quantum eraser. The signal photon flies to the screen and is recorded first, while the idler takes a longer journey before you decide whether to keep or erase which way information. Only afterward do you go back through the data and pair each earlier signal hit with the corresponding idler outcome, and you discover that the sub-ensembles associated with erased outcomes line up into crisp interference, while the sub-ensembles associated with which way outcomes do not, even though your choice came later. That sounds like sorcery until you notice the practical bookkeeping. No one ever sees a visible fringe at the screen without sorting. No message goes backward in time, and no single detection flips after it's made. What changes is the pattern. You can legitimately extract when you condition on what kinds of knowledge your full setup allowed to exist. The eraser's lesson becomes sharper when you try to cheat. Storing which way bits on a hard drive and then deleting them won't bring fringes back, because the damaging act isn't your ignorance, but the fact that the information leaked into the world at all. Once the environment has carried away path clues, countless microscopic degrees of freedom now know, and that diffuse knowledge, called decoherence, kills the phase relationships interference needs in a way you cannot reverse. The real eraser must operate at the quantum level before those clues are dispersed by arranging the optics so that downstream there simply is no measurement that can, even in principle, separate the path stories. In practice, that means recombining, polarization tags, rotating analyzers to mix orthogonal marks, or using beam splitters that make the two histories blur into a single indistinguishable narrative again. If you keep your intuition anchored to the idea of records, the experiment becomes less spooky. Interference is what you get when nature can treat alternatives like two verses of the same song. Which way knowledge is what you get when you pin those verses to different folders. The eraser is you throwing away the folder tabs before they harden into files. There's also a sober guardrail here. Because the fringes only live inside the sorted sub-ensembles, you can't use the eraser to signal faster than light, or to rewrite an outcome already registered. Quantum mechanics protects causality by hiding the usable pattern until you combine both halves of the story. What you're really learning is a new ethic for asking questions of the world. If you interrogate reality in a way that could have told paths apart, you must live with a particle-like account. If you interrogate it in a way that makes the paths impossible to distinguish, you earn the right to a wave-like account. And if you design things so that which account is admissible is decided late, then late it is, because in this domain what is and what can be known are not separable. The human echo is gentle but real. Some meanings collapse when you insist on sorting every thread into a labeled box, and some harmonies appear only when you let certain distinctions go. The quantum eraser doesn't romanticize confusion. It shows you that clarity has kinds, and that one kind, interference, requires you to protect a space where rival explanations cannot be pried apart. In the end, you don't unwrite yesterday. You decide, with exquisite care, whether today's apparatus makes yesterday's alternatives fundamentally inseparable, and in that careful unknowing, the impossible pattern returns, not as a trick, but as the most honest answer a coherent world can give. Wheeler's cosmic delayed choice with quasars. Imagine pointing a pair of telescopes at the night sky and discovering that the universe itself has quietly built you an interferometer the size of a galaxy, a device in which a single ancient photon from a quasar has two viable routes, left side of the lensing galaxy or right, long before Earth had oceans, yet you can wait until that photon finally arrives, and only then choose whether to let those routes recombine into a delicate interference, or to keep them separate as distinct images. And this is the audacious heart of Wheeler's cosmic delayed choice. Not a trick to rewrite history, but a clean way to test whether what you call what happened is fixed by an earlier, path-like tale, or by the present tense question you actually ask of the light. Start with the cosmic stagecraft. A quasar, blazing billions of light years away, emits photons that stream outward through expanding space. Somewhere along the journey, a massive galaxy or cluster sits nearly along our line of sight, and its gravity, curving space-time, not tugging like a string, deflects that light along two large-scale geodesics that wind around opposite sides of the lens before fanning out toward Earth. Under a camera, those separate routes often appear as two quasar images, or, when geometry is just right, as segments of a smeared ring. An Einstein ring, nature's signature that multiple optical paths are available. Wheeler's bold suggestion was to treat those paths as the cosmic analog of the two arms in a lab interferometer. If, at Earth, you use optics to combine the two incoming beams, so that, within the photon's coherence time, their tiny phase, difference matters, then the statistics can show wave-like interference. If instead you keep the beams apart and send each to its own detector, you effectively keep which path information, and interference disappears. The delayed twist is not time travel. It's the idea that you can decide which measurement you perform, now, long after the photons skimmed the lensing galaxy eons ago, and the outcomes will line up with the option you chose. Wave, if you arrange for recombination that erases path distinctions. Particle, if you keep the routes distinguishable. Intuition balks. Surely the photon already went left, or went right, around that galaxy ages before our species existed. But the quantum lesson, sharpened by this astronomical scale, is that a path story you can consistently tell must be compatible with the entire measurement context at detection, not with a classical picture of little bullets picking a side and carrying a postcard of their trip. To make this more than poetry, anchor it in the practicalities astronomers face. Those twin beams do not arrive in lockstep. Gravitational and geometric delays can make one path longer by hours, days, even weeks, which is why lensed quasars are time-delay tools for cosmology. For interference, though, you do not need the two routes to arrive simultaneously across macroscopic spans. You need their phase to be compared within the photon's coherence window, which can be engineered if you work at radio wavelengths, or, in principle, with careful spectral filtering at shorter wavelengths. The atmosphere jitters, the lens galaxy's stars induce microlensing, and the two beams may wander through slightly different intergalactic plasma, all of which can scramble phase in practice, so a pure single-photon, optical band demonstration across cosmological distances is technologically punishing. But that difficulty is a hardware complaint, not a conceptual escape hatch. Radio astronomers already exploit wave optics lensing, where interference fringes from multiple gravitational paths imprint subtle modulations on what we detect, and in the lab, delayed choice tests have repeatedly shown that when you recombine alternatives that remain fundamentally indistinguishable, interference appears, while any principled ability to tell them apart kills the pattern. What Wheeler dramatized with quasars is that nothing in quantum mechanics demands the decision be made early. Nature does not stamp path chosen on a photon as it rounds a galaxy. What counts is whether your final arrangement preserves or erases the possibility of distinguishing the alternatives. This cosmic version also cleanly separates two ideas that often get muddled. First, it does not let you signal to the past or edit a recorded fact. Each photon yields a single detection, here and now, and only the ensemble statistics depend on whether you configured for recombination or separation. Second, it is distinct from the beautiful cosmic Bell tests, where astronomers used ancient quasar photons to choose measurement settings in entanglement experiments. Those tests push back on the worry that the universe conspired with our random number generators, but they are about non-local correlations, not about turning the sky into a giant two-slit. Cosmic delayed choice is about one photon and two gravitationally curved roots, and whether your telescope system treats them as two exclusive stories or one unsplittable narrative. If you want a picture that doesn't mislead, imagine two mountain passes feeding into a single valley road toward your house. At your door, you either build a combiner that merges the lanes so perfectly you cannot tell which pass a traveler used, in which case subtle interference between possibilities can show up in the long-run pattern of arrivals, or you keep the lanes separate all the way to two doorbells and log north versus south. Crucially, your door hardware decision does not shove travelers back up the mountain to pick differently. It determines which description of the journey survives without contradiction in your records. That distinction between stories and signals is where the philosophical bite lives. The universe allows multiple consistent accounts, but only one per arrangement, and your present choice of arrangement picks the account. Nothing retrocausal is required, though some time-symmetric interpretations enjoy the poetic symmetry. The no-nonsense message is that distinguishability and interference are mutually exclusive traits of the whole experiment, from quasar to lens to beam combiner. And there is a quiet, human echo in that immensity. You and I often insist that events, especially distant ones, must carry a single, path-like truth independent of any question we might ask later, as if meaning were a cargo, tag-affixed at departure. Wheeler's Cosmos gently argues otherwise. Sometimes what can be said about a journey depends on the lensing we discover along the way and on how, at the end, we choose to merge or separate the stories that reach us. In the lab, that choice is a switcher to beam splitter. In the sky, it is a design challenge spanning years and instruments. In a life, it is the discipline to know when to keep differences sharp and when to let roots blend. Cosmic delayed choice doesn't grant you power over yesterday. It asks you to notice how profoundly today's questions shape the map you draw of yesterday. And it invites you to look up and realize that even across billions of light years, the universe is willing to play by the same rules. Interference where paths can't be told apart. Clarity where they can. Leaving you with a deeper respect for the difference between changing the past and choosing, with care, the frame in which the past becomes legible. Retrocausality models, signals from the future. What if the arrow of time doesn't always slice forward like a knife, but sometimes bends just enough to whisper back, quietly, lawfully, never loudly enough to let you phone yesterday, so that the future helps choose which pasts were even possible? That is the core question behind retrocausality models. An umbrella for ideas that try to explain quantum puzzles by allowing limited influences from later events to help determine earlier microscopic facts without opening the door to paradoxes or casino-breaking time machines. And the reason physicists flirt with this strange option is simple. Our best dynamical equations are largely time-symmetric, yet our stories about cause and effect are not. So perhaps the asymmetry we feel is not written into the laws, but into the boundary conditions we impose, what we take as fixed in the past and up for grabs in the future. In the ordinary picture, causes push forward, and measurements merely reveal what was already settled. In a retrocausal picture, measurements can behave like future boundary conditions, gently constraining how the earlier quantum variables must have been arranged so that everything hangs together consistently when the dust settles. That sentence sounds like metaphysics until you recall everyday systems solved by boundary conditions at two ends. A guitar string's allowed vibrations are picked not by what it was doing a moment ago, but by the requirement that it fit both clamps at once. A ray of light through a lens seems to know where it will end up, because only certain families of paths satisfy the start and end constraints. In the same spirit, retrocausal models ask you to treat a quantum experiment as an all-at-once problem where initial preparation and final measurement together select a story that respects the equations everywhere in between. The practical lure is that this move can tame quantum weirdness without invoking faster-than-light influences across space. In bell-type setups, for instance, instead of saying one wing instantly telegraphs to the other, you let each wing's later measurement setting feed backward into the local past, so the correlations show up because the hidden variables were never independent of those settings in the first place. No spooky action, just a subtler bookkeeping in time. To keep your feet on the ground, separate retrocausation from the cartoon of signals from the future. A signal is a controllable pattern you could modulate to send a message. Retrocausal models don't hand you that dial. They usually preserve the no signaling rule. You cannot exploit the setup to encode a bit today and decode it yesterday, because any backward-pointing influence is buried inside a global consistency condition that only shows up statistically and only after you include all the right pieces of the experiment. Think of it like a crossword whose final down clues restrict what letters you must have chosen earlier in the across clues. The finished grid reflects influences that point both ways, but you can't use that to fax a secret to your past self, because a single letter never tells the tale. Only the completed puzzle does. Concrete proposals make this more vivid. In the transactional picture, a quantum exchange is described as a handshake between a wave that goes forward in time and a solution of the same equations that goes backward, with an actual event occurring, only where the two agree. Nothing gets rewritten and no loop breaks causality, because the handshake is one consistent transaction determined by constraints at both ends, not a signal that you can alter after the fact. In time-symmetric boundary approaches, you model the experiment by picking an initial distribution and a final filter, then solve for the in-between variables that satisfy both, which naturally produces the strange but measured correlations while keeping everything local in space. What looks like non-locality becomes non-separability across time. And in modern causal model language, you draw arrows that include a subtle backward link from the measurement setting to the hidden variables. Done carefully, this removes the need for fine-tuned conspiracies while still blocking any channel you could use for messaging, because the statistics refuse to budge unless you condition on all the variables you do not control. The immediate objection, grandfather paradox, misfires here because these models don't add a new wire you can tug to force the past to change. They replace the step-by-step narrative with a global constraint narrative in which only self-consistent histories occur, full stop. If you try to promote the backward influence into a communication line, you run into the same wall every time. As soon as you average over the parts of the setup you don't get to fix, the backward-looking correlation washes out into ordinary noise. That's why labs do not see signable patterns in delayed choice or quantum eraser experiments. You can sort earlier data into revealing sub-patterns once you know the later settings and outcomes, but you cannot produce a readable message at the earlier station by flipping a switch at the later one. The deeper reason is that thermodynamics and information flow still point forward. While the micro laws may be time-symmetric, the universe's low entropy past gives you a practical arrow that makes prediction easier than retrodiction, and retrocausal models respect that. They tweak the explanatory direction of certain quantum accounts without touching the hot to cold, memory to record, cause to evidence gradient that runs your everyday life. If anything, they ask you to be more careful with the word cause. In the interventionist sense, what happens if I wiggle this knob? Causation remains forward, because interventions are defined as variables you can set independently, and retrocausal dependencies precisely deny you that independence for the hidden variables. What points backward is not a usable push, but a constraint that becomes visible only when you condition on the final context. Why bother with all this gymnastics? Because it offers a clean way to accommodate three desiderata that otherwise fight: keep relativity's ban on faster-than-light signals, explain Bell-type correlations without positing unreachable parallel worlds or action at a distance, and avoid the heavy price of superdeterminism, where every choice you think you make was pre-wired into the initial state of the universe. Retrocausality says, let your choices be free at the pragmatic level, but let the microscopic variables be correlated with those choices through lawful, time-symmetric boundary conditions. It's not a proven fact of nature. No interpretation is, but it is a coherent competitor, and it suggests testable styles of thinking. Seek experiments where adjusting the final filter changes which earlier variables are even meaningful to talk about. Analyze quantum networks with causal arrows allowed to bend. Look for scenarios where time symmetry plus two boundary constraints predicts subtleties that a purely forward stochastic model would miss. Even when those experiments collapse back onto the same numbers, they teach you the crucial distinction between a narrative and a signal. You may rewrite the story you can consistently tell about micro-events when you include later facts, but you cannot use that storytelling freedom to call your past grandmother. If all of this still feels esoteric, turn the lens inward for a softer analogy that doesn't cheat. Every diary you write is retrocausal in a harmless sense, because the questions you ask today determine which fragments of yesterday you even count as relevant. Nothing in the past has changed, but which earlier details become the facts depends on the frame you adopt now. Retrocausal models claim something structurally similar at the quantum level, where the frame is made of apparatus and boundary conditions, not feelings. They are not invitations to mysticism. They are reminders that physics is often solved at the level of constraints, not pushes. The ending doesn't bully the beginning. The ending and beginning co-author a single, self-consistent middle. So, are there signals from the future? Not in the sense that lets you hedge a stock or save a vase. The signal you could steer remains forbidden by the very rules that make the models work. But there may be whispers, from later choices into earlier microfacts, that ensure the world's ledger closes without fictions or superluminal debts. And learning to hear that possibility doesn't make you a time traveler. It simply makes you more fluent in a universe where the laws don't pick a favorite direction, and where the stories we tell about cause, evidence, and explanation are still catching up. Quantum switch. When before-after breaks. You've been trained since childhood to trust sequences, to make the bed before breakfast, to turn the key before the engine starts, to believe that even when events are messy, they're still stacked like books on a shelf. So the first time you meet the quantum switch, it feels like a prank. The universe plays on your sense of order. Two operations that ought to happen in a definite sequence are applied to a single quantum system in such a way that the order itself is in superposition. So there is no fact of the matter about whether A happened before B or B before A, until you force the question. And in that in-between, your idea of before-after quietly breaks. Begin with a down-to-earth image. In an ordinary recipe, adding milk then coffee is not the same as coffee then milk. The taste and texture differ because mixing isn't perfectly reversible. Sequence matters. In technology, sequence also matters. A message sent through two devices gets processed in one order or the other. And if the devices are noisy, those errors add up differently depending on which comes first. Classical physics makes you pick. Even in quantum labs, most circuits still wire gates in a fixed order, one after another. The quantum switch is the move that refuses to pick. You let a control system, often the polarization or path of a single photon, decide the order in which a target system passes through two black boxes A and B. If the control is up, the target experiences A then B. If down, it experiences B then A. And if the control is prepared in a genuine quantum superposition of up and down, the whole device implements A then B and B then A at once, woven together so tightly that no underlying timeline exists that could consistently assign one order to every run. What you get at the output is not a coin flip between two sequences. It's a coherent combination whose interference can be tuned and read, revealing patterns that can't be reproduced by any mixture of definite orders. This is not a word game, but an operational resource. With the switch, there are tasks you can accomplish with fewer queries or with higher reliability than any setup that fixes the order in advance. For example, suppose two mystery devices either commute or anti-commute. In a fixed order world, you must probe both orders to find out which case you're in. With the quantum switch, a single use of each device inside an indefinite order can imprint the answer onto the control system, letting you solve the problem with fewer interactions. Or consider communication through noise. If two nasty channels normally would erase your message, an indefinite order of passing through them can partially cancel the damage, recovering information a fixed order would lose. These advantages are not loopholes. They're proofs that order can be a quantum resource to be engineered and spent like energy or entanglement. What does a real device look like? In optical experiments, researchers send single photons into an interferometer whose two arms are physically different sequences of the same pair of devices A and B. One arm implements A then B, the other B then A. The photon's path acts as the control. Its polarization, or some other degree of freedom, is the target being processed. When the paths are recombined, the two histories interfere. If the control is prepared in a superposition of paths, the photon effectively experiences an indefinite order, and by changing phases or internal settings, you make the combined effect tilt one way or the other. Crucially, this is all local in space. There's no faster-than-light trickery, yet it is genuinely non-separable in time. You cannot write the overall transformation as first X, then Y, without contradicting what the statistics demand. To certify that you really built something with no fixed order, you don't rely on an anecdote. You use a diagnostic called a causal witness, a test function measured on many runs that becomes negative only if the process cannot be decomposed into any mixture of atom B and B then A. When experiments see that negative value, they haven't disproved causality in the everyday sense. They've shown that causal order, which event is before which, need not be a background constant at the quantum scale. That phrase is unsettling until you put it next to ideas you already accept. You know quantum states can be superpositions of locations or energies. You know systems can be entangled so their properties don't belong to either part alone. The quantum switch is the same pattern raised one level up. Not where is the particle, but what is the order of the operations, is treated as a controllable quantum property able to interfere with itself and to generate advantages when harnessed. The technical moral matters for the future of computing and communication. Circuits that allow indefinite order, sometimes called process-based or order-free architectures, can reduce the number of times you need to consult a black box subroutine, potentially cutting resource costs in algorithms that sort, classify, or compare transformations. In metrology, a switch can turn the nuisance of sequence-dependent noise into a handle, letting you distinguish devices more sharply or estimate parameters with fewer photons and less damage. In networks, it hints that routing information through quantum switches could raise capacity in stubbornly lossy regimes. None of this says order is always better when it floats. Many tasks gain nothing, and building switches that work beyond tabletop optics, say with atoms, ions, or superconducting circuits, comes with hard engineering trials. Keeping coherence intact across both orders, aligning devices so that one and the same particle truly experiences them in both sequences, and scaling the idea so it's not a laboratory showpiece but a workhorse. Yet the concept has already survived the skeptical gauntlet. Teams have demonstrated photonic switches that pass causal witness tests, verified query savings on small tasks, and shown resilience advantages against certain kinds of dephasing. Even the objections teach you something precise. A skeptic says, surely there's still a hidden underlying order, we just don't know it. The data replies, if there were, any mixture of those hidden orders would obey bounds the switch blatantly surpasses. Another says, isn't this just parallelism? No, because parallel devices still have a well-defined graph of precedence. The switch erases the graph edges themselves. Order is not chosen and then hidden. It is genuinely not set. What does this do to your everyday picture of time? It doesn't let you uneat breakfast or dodge responsibility. Macroscopic arrows still arise from thermodynamics, records, and the way information spreads, but it does invite a finer humility. The categories you treat as absolute, first, then, cause, effect, may be emergent conveniences rather than granite foundations, and at small scales you can choose hardware that enforces them or hardware that loosens them. The philosophical echo is gentle but useful. Sometimes your life improves not by reordering steps, but by questioning whether the steps needed a single order at all, by holding two possibilities in tension long enough for a better pattern to emerge. The quantum switch is physics' way of making that move literal. Keep the roots coherent, withhold the verdict about what came first, and you unlock options unavailable to either fixed order alone. In the end, before-after hasn't died. It has become a tool you can switch on and off. And once you see that, you stop treating time's grammar as a cage and start treating it like code. Sometimes linear, sometimes braided, written, not only to describe the world, but, in the lab, and someday in your devices, to shape what the world can do. Wigner's friend. 2 truths, 1 experiment. Imagine sealing a tiny lab like a snow globe and asking your smartest friend to go inside, measure a lone quantum system, and write down what they see, while you wait outside promising not to touch a thing. Minutes later, you claim the entire snow globe, friend, memory, notebook, air, can still be treated as one coherent quantum object that has not yet decided, and Wigner's friend is born from that quiet standoff. 2 observers, 1 experiment, and 2 incompatible but individually sensible stories about what is real. Inside the globe, your friend follows the textbook. Prepare, measure, record. The needle points left or right. A number gets inked. And for them, the uncertainty is over. There is a definite outcome now filed under fact. Outside, however, you refuse to place the famous cut between quantum and classical at the lab door. You treat the Friend Plus system as a single unit evolving smoothly like any other quantum system, which means that, so long as the globe has been perfectly isolated, there remains a live possibility to perform a clever interference test on the whole package and reveal that the Friend's lab sits in a delicate superposition of saw left and saw right. This is not about peeking and seeing both numbers at once on the same page. It is about designing an operation that would only succeed if the 2 macroscopically different lab states have not irreversibly leaked their telltale differences to the environment. If such an operation worked, your outsider story, no collapse yet, would be vindicated. But the insider story, collapse happened, has already shaped a human experience. Can both be true? The thought experiment forces you to notice that fact in quantum mechanics can be uncomfortably perspectival. What is settled for one observer may remain unsettled for another who has not yet interacted in a way that prevents interference. The tension is not that someone is wrong about a registered click. It is that the grammar you use for clicks, records, and reality depends on where you decide to place the boundary between system and observer. And Wigner's friend shows that boundary is not dictated by the equations. It is chosen by you. To see how sharp this is, strip away romance and follow the mechanics. Your friend's measurement is, at bottom, an entangling interaction. The system's 2 possibilities become correlated with 2 different brain plus notebook states. If, immediately after, you could reverse those correlations, think of it like unmeasuring by running the process backward, or by performing a joint operation on the globe that recombines the 2 alternatives, you would recover interference, proving that, from your vantage point, Nothing irreversible had happened. That does not mean your friend was fooled. It means their outcome was a local fact relative to the information they had and the interactions they underwent. In real life, of course, the snow globe isn't perfect. Air molecules bump, photons scatter, heat flows, and this relentless decoherence spreads the which outcome marks into the environment so widely that no one can gather them up again, which is why you and I do not watch tables wobble between positions or observers smear between opinions. But decoherence, powerful as it is, only explains why interference becomes practically hopeless. It does not tell you whether a single, observer-independent outcome exists in principle once macroscopic records form. Wigner's friend keeps that question open by imagining an almost impossible lab that is isolated well enough for the outsiders' interference test to be feasible. And modern quantum processors nudge the thought experiment toward reality at a toy scale. An inside friend can be a small register that measures a qubit and stores the result. An outside Wigner can then run a joint operation on both registers to check for the telltale coherence that would be impossible if a final collapse had already occurred. These demonstrations do not put human beings into superposition, but they prove the logic is not mere wordplay. Whether the global process admits interference depends on how completely you have prevented information about the outcome from leaking away. Confronted with the standoff, physicists sort themselves by which promise they refuse to break. If you insist that the equations are universal and never produce a literal collapse, you land near the many worlds view. The inside observer experiences a definite result because they travel with one branch, while the outside observer can, in principle, still reveal coherence by acting on the pair of branches together. There is no contradiction because two truths live on two non-communicating slices of the world. If you instead insist that statements about quantum states are always about an agent's expectations and information, not about mind-independent properties, you'll like agent-centered approaches. Your friend and you assign different states. Because you have different data, and there is no single global truth to compare until you interact and exchange records. When you do, your stories reconcile in the usual way, and no paradox survives. If you insist that there must be one outcome for all, and that physics should say where quantum stops, you favor objective collapse stories. When measurements involve enough mass or complexity, spontaneous processes break superpositions whether or not anyone is watching. So Wigner's interference is not just hard, but impossible in principle. And the friend's fact is universally true. A fourth path, relational thinking, takes the perspectival lesson literally. Facts are relations between systems, not monoliths pinned to the world. Your friend's statement is true relative to them. Your interference statement is true relative to you, and only when you meet do you create a new relation with its own facts. You do not have to pick a camp today, but you do have to notice that each choice trades one kind of comfort for another. Universality of the equations versus universality of outcomes. Objectivity of facts versus objectivity of the rules. There is a tempting overreach. The paradox invites, and you should resist it. Wigner's friend is not a license for anything goes, or a declaration that truth is optional. It is a disciplined reminder that who can claim what depends on the web of interactions that make that claim testable. Your friend cannot later be made to remember both answers. You cannot extract interference once the world has copied the outcome into a billion uncontrolled degrees of freedom. There are hard limits that protect consistency and forbid retroactive editing. What changes is your ontology, not your bookkeeping. You stop imagining that a single narrative, valid for all observers at once, is required by the theory. The grander no-go results that build on Wigner's friend, where multiple outside observers and nested labs are arranged so that assuming one shared set of observer-independent facts leads to contradictions, push this point even harder. But the seed is already here. Facts may be more like agreements forged by interaction than like stones scattered in a field waiting to be found. And yet, the thought experiment also softens into something humane. How often in your life do you confuse your private record for the whole story? insist that your vantage point is the only one with access to reality, and slam the door on reconciliation before the conversation, the interaction, has happened. Wigner's friend suggests a different discipline. Keep track of what is true for you without denying that a different, consistent truth may exist for someone else until the two of you engage. When you finally do, the combined evidence fixes a shared account. Just as the outsider opening the globe and talking to the insider collapses two narratives into one. The ending is not mystical. It is modest. Quantum theory will keep working, whether you prefer one interpretation or another, and your kitchen will not start violating causality. But if you let Wigner's friends sit with you, you acquire a new habit of mind. Treat facts as claims tied to interactions, notice where your cut is, and remember that sometimes the path to a common truth is not to shout louder, but to arrange. The meeting where interference is no longer possible and agreement at last is. Frauchiger, Renner. Theory versus itself. You expect a good theory to be like a clean mirror. Whatever you point it at, including itself, should come back sharp and consistent. Yet the Frauchiger-Renner thought experiment holds that mirror to quantum mechanics and finds a hairline crack. Under three very reasonable-looking commitments, the theory generates two incompatible certainties about the same event, as if truth forked inside one and the same experiment. The setup scales Wigner's friend into a nested puzzle with two sealed labs and two outside Wigners, plus a deliberately mischievous quantum coin. Inside the first lab, an agent measures the coin and, depending on the result, prepares a spin for the second agent in the second lab to measure. Outside, each Wigner reserves the right to treat the entire lab they're not opening, not only the particle, but the friend, apparatus, and notebook, as one big quantum system that can still in principle display interference. Now, the plot twist is not mathematical pyrotechnics, but careful bookkeeping of what each agent is licensed to conclude if quantum rules apply universally. If the first friend obtains a certain coin outcome, they become sure that the second friend will not see a particular spin result. Knowing how the preparation works, the second friend, upon seeing their own result, becomes certain that the first friend must have seen the opposite coin outcome. Each outside Wigner, in turn, designs a measurement that, when it clicks, OK, implies they can be certain about what the inside friend must have recorded earlier. String these perfectly sensible inferences together, and you arrive at a striking declaration. Given what I saw, the other Wigner cannot possibly see. OK, but here's the sting. The quantum calculation for the whole, meticulously isolated four-agent process assigns a small but non-zero chance that both Wigners will get OK on the same run. So the theory itself tells you that the event every agent's reasoning has ruled out will sometimes occur. That is the paradox in its cleanest form. Under three assumptions, single world, universal validity, and a consistency principle, you can prove that quantum mechanics predicts a joint outcome that the same quantum mechanics lets ideal agents exclude with certainty. No amount of hand-waving about "it's just weird" heals that. Something in the trio must give. Notice what the result is not saying. It is not that real experiments have recorded logical contradictions, or that human consciousness collapses wave functions. The agents in the theorem are abstract reasoners with perfect knowledge of the experimental design, and the labs are imagined to be so well isolated that the outside measurements could, in principle, recombine alternatives that would normally decohere away in everyday life. Within that idealized world, the contradiction is surgical, and it forces you to choose what you value more. Do you keep a single observer-independent outcome and restrict quantum theory's domain, perhaps by positing objective collapses that kick in for macroscopic devices so Wigner's interference is impossible in principle? Do you keep universal validity and abandon the idea that there is one outcome for everyone, stepping into a many-worlds narrative where each agent's certainty lives on its own branch and the two OKs are not in the same world after all? Do you soften the consistency rule and say that A is certain that B is certain, does not license A to adopt B's conclusion unless their records have actually interacted? an agent-centered move that keeps each viewpoint tidy but denies a single global ledger of facts until observers meet and compare notes? Or do you lean into relational thinking, which says facts are always about relations between systems, so statements that look contradictory are only so when you try to promote them to a view from nowhere that the theory never promised to provide? Each escape route has a price tag. Objective collapse stories must specify when and how the collapse happens without ruining microscopic successes. Many worlds must explain what probabilities mean when everything happens. Agent-centered and relational approaches must convince you that giving up transitivity of certainty is not giving up on truth, but giving up on a kind of truth no experiment can require. What makes Frauchiger Renner valuable is not that it crowns a winner, but that it cleans the table. Quantum theory can be extended to observers, or it can be single world for everyone. It can be globally consistent across nested viewpoints, or it can be strictly local to each vantage point, but it cannot be all three at once. In other words, the crack in the mirror is a map. You get to decide which edge to polish and which to accept as a seam. This matters beyond philosophy. Smaller, controlled versions of the logic have been enacted on quantum computers, where qubits stand in for friends and Wigners. They don't put people into superpositions or resolve the paradox with a single measurement, but they demonstrate the algebra of inference that the theorem uses and show you why appeals to common sense about outcomes won't fix what is. At heart, a clash between universal rules and a global notion of shared facts. And it matters to you personally because it asks you to check a habit. The reflex to treat your own certainty plus your model of someone else's certainty as a license to close the case before you actually meet and compare records. The safest conclusion to carry out of this snow globe world is modest and sturdy. Quantum mechanics works spectacularly well, but when it describes agents describing experiments, the glue holding everyone's facts together is not guaranteed. By mathematics alone, the glue is the interaction where records become shared. Until then, there can be two truths inside one experiment without chaos, because the theory that predicted both also predicted the friction you feel trying to merge them. The paradox does not break physics. It breaks a comfortable picture of a single God's eye diary of events, and it leaves you with a choice that is as clarifying as it is uncomfortable. Decide what you are willing to relax: universal reach, single outcome, or cross-observer certainty, and then learn to live and reason with the world that choice makes. Measurement loops. Who observes the observer? You're used to thinking of a measurement as a one-way street, an eye looking at a scene, a sensor sampling a signal. But the moment you bend that street into a circle so that the outcome of a measurement tweaks the very device that did the measuring, and that tweak changes what gets measured next, and so on. You've stepped into the unsettling terrain of measurement loops, where the question, who observes the observer, stops being philosophy and becomes hardware. In a classical feedback loop, the idea is familiar. A thermostat reads the temperature and switches the heater. The new temperature feeds back into the next reading, and the loop stabilizes the room. The measurement doesn't rewrite the air, it just reports it. In the quantum world, the loop is qualitatively different, because a measurement is never a purely passive peak. It creates part of the fact it reports by disturbing, updating, or steering the system it touches. Wire those updates into a loop, and you don't just stabilize a variable, you sculpt the very state of a system, sometimes conjuring behaviors no fixed one-way measurement could produce. Start with the basic ingredients. A quantum measurement is not just a number on a screen. It's a physical interaction that entangles the system with a measuring device, and then lets some record of that interaction leak into the environment. That leakage, tiny flashes of light, vibrations, electronic clicks, both makes the record robust and robs the system of the delicate phase relations that would otherwise let different possibilities interfere. In a loop, you use the record before it fully spreads. You read a bit of information and feed a fast control signal back onto the system, or even back onto the meter itself, changing how the next sliver of information will be gathered. If the loop is swift and gentle, you enter the realm of continuous monitoring, where a stream of weak, partial measurements produces a jittering but lawful trajectory of the system's state, and feedback nudges that trajectory toward a target you choose. This is how experimentalists cool a vibrating nanobeam closer to its quantum ground state by watching it and pushing against its motion in real time. It's how they stabilize a fragile superposition in a superconducting qubit by repeatedly checking a multi-qubit property and correcting tiny slips without ever looking at the actual value that would collapse the superposition. It's how they lock the phase of a light field or keep a single ion spin aligned against random drifts. The loop doesn't magically avoid disturbance. Every read still pokes the system, but by choosing what you read and how you respond, you bias which kinds of disturbance you suffer and harvest the information that helps you undo it. That is the first surprise of measurement loops. Instead of treating back action as damage, you engineer it into a tool. Now close the circle one notch tighter and aim it at the question in the title. Who observes the observer? In a lab, you can literally build the observer into the loop. Let a pro be Asia, a system. Then let a second stage observe the probe and, depending on that observation, change the probe's future sensitivity or even rewrite its local reference frame. You've made the meter adaptive. It learns from its own output. Do this inside an interferometer and you find possibilities a static device cannot offer. The apparatus can choose, mid-flight, which basis it's effectively measuring in, or whether it's reading a joint property of two subsystems rather than either one separately. Crucially, no paradox follows from this self-inspection, because quantum theory already forbids the two impossibilities that would generate contradictions. You cannot copy an unknown state perfectly, and you cannot read out two sharp, incompatible properties at once. Those limits act like guardrails for self-observation. Try to design a loop where the device measures a property that guarantees a certain next outcome, and you'll discover the rulebook quietly changes the game by adding noise, by rotating the basis, by spreading the information you want in 2 degrees of freedom you didn't control, until the loop finds a consistent fixed point. Physicists give this intuition different clothes depending on taste. Some talk about the loop settling into a steady state selected by the measurement and feedback. Others analyze causal consistency and show that when you draw the arrow diagram for a loopy process, only processes that admit a self-consistent assignment of probabilities can ever be realized. Either way, the moral is the same. Asking a device to observe itself does not break the world, because quantum mechanics refuses to grant the kind of perfect, non-disturbing mirror that would make a liar's loop possible. These loops are not just curiosities, they're becoming workhorses. In quantum error correction, for example, the life of a quantum memory depends on a loop that repeatedly measures multi-qubit syndromes and uses the results to nudge the hardware back on course without learning the stored data itself. The measurement here is not a final verdict, but an instrument. It tells you just enough about the error to fix it, while the loop structure ensures the data's logical state is never directly observed and therefore never collapsed. In quantum metrology, loops let you beat noise you can't avoid. Suppose two kinds of disturbances scramble a phase you want to estimate. By watching a proxy in real time and feeding back, you can cancel part of one disturbance and convert what's left into something your estimator handles better, effectively trading uncontrolled noise for structured, correctable noise. In cavity optomechanics and circuit QED, the setup itself is a built-in loop. Light inside a cavity measures the position of a tiny mirror or the frequency of a superconducting circuit, while that very act of measurement exerts a force back on the thing being measured. If you don't manage the loop, the back action can heat and blur. If you do manage it, the loop damps motion, cools vibrations, and even creates non-classical states of motion that no open-loop measurement would leave behind. And at the frontier, researchers explore loopy quantum networks where operations do not have a single global order, yet still avoid paradox. Networks that route quantum systems through devices in patterns that cross and return with consistency, enforced not by a hidden time traveler, but by the same two guardians as before: imperfect copying and complementarity. All of which brings us back to the humane reading of who observes the observer. When you and I tell stories about facts, we smuggle in a picture of a ladder, the world at the bottom, then a series of ever more detached observers climbing the rungs, each one looking at the one below without being changed by the glance. Measurement loops teach you that the ladder is sometimes a circle, and circles demand a new honesty. Your questions shape not only what you can learn, but also what the next sensible question can be. Your instruments are part of the world they report on. If you treat them as outside, your stories go brittle. The cure is practical and philosophical at once. Design your loops so the information you harvest is exactly what your goal needs. Accept that every look has a cost and use feedback carefully to pay that cost where it hurts least and helps most. In a quiet sense, that is what science at the quantum edge already does every day. It stops pretending that observation is a neutral mirror and instead engineers observation as a process with knobs, delays, and returns. The conclusion is not mystical and not bleak. You are not trapped in a hall of self-watching mirrors. You are offered a set of principles for making those mirrors useful. Read early, feedback fast, measure the thing you can correct, stay blind to the thing you must preserve, and build your devices and your explanations so the loop closes on a consistent shape. When you do, the ancient riddle of who observes the observer doesn't dissolve. It matures into a craft, learning to listen to a world that listens back, and learning to ask it questions in a way that makes both of you wiser the next time around. Time-Symmetric two-state vector formalism. Open a mystery novel and read it in the strangest way you can imagine, not straight through from page 1, not by peeking at the last chapter for spoilers, but by letting the first chapter push forward while the final chapter pulls backward, so that every sentence in the middle is shaped by what came before and what you now know will come after, and you have the flavor of the time-symmetric two-state vector formalism, a way of describing a quantum system between preparation and detection that treats the past and the future as equal partners in fixing what can sensibly be said about the present. In the usual classroom picture, you prepare a state and let it evolve until you measure it. The initial condition gets pride of place, and the final outcome is a surprise the universe serves at the end. The time-symmetric view refuses that one-way story. It tells you that if you later post-select a particular outcome, meaning you keep only those runs where the detector clicked a certain way, the system in the in-between period is most honestly described by two boundary arrows. One state, evolving forward from the preparation, and a second state, derived from the successful post-selection, evolving backward from the future measurement toward the past. Nothing supernatural is smuggled in here. You are not sending messages to yesterday or rewriting what happened. You are simply conditioning your description on both the entrance and the exit of the experiment, the way a bridge is designed from both banks at once. With both boundaries in hand, you can compute how likely any intermediate measurement would have been and, crucially, you can probe the system between those boundaries so gently that you scarcely disturb it. This is the realm of weak measurement, in which the apparatus samples a property so lightly that each single read is noisy, but the average over many runs reveals a crisp tendency. When you apply weak measurement within the two-state picture, and then keep only the members of the ensemble that pass the final post-selection, the number that governs the tiny shift of your meter is called a weak value, and it encapsulates how the earlier preparation and the later filter together tilt the statistics of the middle. That number can look bizarre at first sight. It can sit outside the range of the ordinary outcomes you would expect from a strong, projective measurement. In optical experiments, it can even come out effectively negative for a quantity that is usually thought of as counting how much of something there is. And this strangeness is why the formalism is worth your time. It teaches you that a high, weak value is not what the particle really had in the classical sense, but a conditional hallmark of interference between alternatives that survive both the beginning and the end of your selection. If you demand a picture you can carry without equations, use this. The preparation lays down overlapping possibilities like translucent slides. The post-selection chooses a particular way those slides are to be stacked. The weak value is the small nudge your gentle probe feels because of the way the stack is aligned by both choices. The most persuasive part is that this is not just philosophy. Laboratories have learned to use the effect. In precision optics, researchers have amplified tiny beam deflections by arranging a preparation and a nearly orthogonal post-selection, so that the weak value becomes very large, turning a whisper of a shift into a measurable drift on a camera, without violating any limits, because the price you pay is discarding most runs that miss the post-selection. In other experiments, careful, weak probing, conditioned on a final filter, has been used to directly map features of a quantum state in a way that complements the usual tomographic reconstructions, and to draw average flow lines for light in a double-slit type setup, lines that do not claim to be literal trajectories of single photons, but that offer a concrete visualization of how probability current distributes when both entrance and exit are fixed. Solid-state groups have adapted the same logic to superconducting circuits and spin systems, where gentle, continuous monitoring can be paired with a final sieve to extract weak values that diagnose coherence or reveal subtle couplings. Through all of these, the guardrails hold. You cannot use post-selection and weak values to send a controllable signal backward in time because you cannot guarantee the desired post-selection on demand. You only learn something special about those rare runs where the end and the beginning happen to line up the way your analysis assumes. In other words, the future is not bossing the past. Your bookkeeping is acknowledging that both ends matter, for the slice in the middle you choose to talk about. Once you let that sink in, several knotty quantum puzzles become less abrasive. Why do some conditioned averages seem to defy classical bounds? Because you are averaging over a finely filtered sub-ensemble whose surviving pathways interfere in a way the unfiltered sample never would. By throwing away the majority of runs, you create a delicate pattern among the survivors that a heavy-handed probe would have demolished. Why do the results depend on the exact final question you ask? Because the final filter is part of your definition of the system in between, just as the shape of a river carved between two towns depends on the positions of both towns. Why does the formalism feel natural in a world whose equations are largely time reversal symmetric? Because it uses that symmetry rather than fighting it, assigning no metaphysical privilege to the initial slice, the asymmetry of our daily lives. The way we remember the past but not the future comes from thermodynamics and records, not from a requirement that physics be blind to the end of an experiment. And why do debates flare about whether weak values are real? Because they tempt you to anthropomorphize them as hidden properties of single systems, when they are better understood as operational numbers that tell you how a particular meter will respond under both conditions you imposed. You can see the sanity check in every credible experiment. Change either the preparation or the post-selection and the weak value, and thus the tiny meter shift changes too, even though no one claims the meter was reading a secret classical variable. The practical moral is generous. If you want to measure without breaking, weak strategies guided by two-state logic let you peek at fragile systems and still keep them useful for what comes next. This is why weak, repeated checks can stabilize quantum memories or help you steer a sensor to its most informative operating point. If you want to see the invisible, post-selection can turn sub-pixel changes into macroscopic motions, trading data rate for clarity in a way that is often worth it when noise would otherwise swamp your signal. And if you want to think more clearly about quantum causation, the two-state formalism gives you a language where what is the system like between two events has a precise, testable answer that does not require you to abandon the symmetries of the laws or pretend that measurements are passive. The human echo is quiet but valuable. You already live parts of your life this way, where who you are in the middle is constrained by what you set in motion earlier and by the commitments you choose to honor later. Your present becomes legible when viewed from both ends. Physics does not romanticize that feeling. but it does legitimize a version of it. Sometimes the most faithful description of now is the one that respects both how you began and how you decide to end. So the next time the quantum world seems to twist your sense of time, remember the novel read from two sides. No page is changed by your reading order, yet meaning blooms when the beginning and the ending meet, and the sentences in between stop being puzzles and become a story you can finally follow. Entanglement, swapping without touching. Picture two pairs of dancers who start the night with their own partners. Then you, the choreographer, take one dancer from each pair into a side room, whisper a joint instruction that fuses their roles together, and when they return you discover that the two people who never met on the floor now move in perfect step as if they had practiced for hours. That is the operational heart of entanglement, swapping without touching. You begin with two independent entangled pairs, never let the remote members interact, and by performing one carefully chosen joint measurement on the middle partners, you create entanglement between the far partners as a conditional, verifiable outcome. Here is the clean sequence without mystique. Start with two sources that each produce a pair of systems with strong quantum correlations. Photons are the workhorse, but trapped ions, neutral atoms, and solid-state qubits can play too. Label them A, B, and C, D. Keep A and D far apart. Bring B and C together in one station you control. On B and C, you do not measure them separately. You perform a joint test that asks, are these two as a pair in one of the special maximally entangled patterns? This test does two things at once. It discards information about B and C as individuals, and it projects the pair BC into one of a small set of tightly knit joint patterns. When that projection succeeds, and importantly, you have a detector flag telling you which joint pattern it landed on. Something remarkable follows from the logic of quantum correlations. A and D, which never touched and may be kilometers apart, are now themselves entangled in a pattern that depends on the flag you observed for BC. If you tell the holders of A and D which flag you saw, they even know which flavor of entanglement they share or which simple local correction to apply to align it with their target. Nothing non-local is signaled to force A or D to change on command. The entanglement is heralded, meaning your local click announces that the joint state of the distant pair has the special non-classical correlations you wanted. This, creating a bond by measuring the middle, sounds upside down until you remember that entanglement is not a substance that flows along a wire. It is a structure of correlations across a whole system. The joint measurement on B and C doesn't ship anything to A or D. It rearranges the correlation book so that A's strongest partner is no longer B and D's is no longer C. The measurement fuses the middle links and leaves the ends sharing the thread. With photons, the hardware looks like this. Make the two middle photons indistinguishable in color, timing, and spatial mode. Interfere them on a beam splitter so that certain two-detector coincidences only occur if the pair occupies a particular joint pattern. Those coincidences are your Bell projections. Because linear optics cannot deterministically distinguish all four entangled patterns, you succeed only on a subset of trials. But when you do, the far pair AD has the correlations you need, and modern detectors timestamp and label those successes, so the remote stations can keep only the good shots. In practice, this requires exquisite matching, laser-locked sources, fiber delays to picosecond precision, filters to erase distinguishing marks, and often the use of a hallmark effect called two-photon bunching to certify the middle interference is genuine. Yet the payoff is decisive. You can knit long-distance entanglement without ever letting the distant systems meet. Why does this matter? Because it turns entanglement from a fragile lab curiosity into a network resource. Over fiber or free space, single photons die off with distance. Trying to share entanglement directly between two distant labs quickly sinks under losses. Swapping solves the scaling problem by dividing the link into manageable spans, creating entanglement on each span, and then performing Bell measurements at junctions to swap the entanglement along the chain. Stack these swaps in stages, and you have the core of a quantum repeater, a way to extend entanglement far beyond the raw attenuation limit, enabling secure key distribution that can be certified device independently, teleportation of quantum, states between distant processors, and distributed sensing where several nodes behave like parts of one shared instrument. In the solid-state world, swapping lets you bridge disparate technologies. A memory qubit in Diamond can emit a photon that meets a photon from a trapped ion. Their interference heralds entanglement between the memories, even though the memories never touch. In modular quantum computing, swapping offers a way to couple small, high-fidelity core chips into a larger machine where entanglement is routed like an addressable commodity, which is deeply different from shipping classical data. Because the correlations you route cannot be replaced by shared randomness without breaking the quantum advantages they underpin. Alongside the promise comes honest engineering pain. The middle measurement only works if the two middle systems are indistinguishable in every way your apparatus can sense. Any hint about which middle photon came from which source kills the needed interference. Synchronization is unforgiving. Picoseconds matter for photons, while memories must hold their states for milliseconds or seconds so you can wait for heralds to arrive from other links. Loss and noise pile up, so you often combine swapping with purification steps, sacrifice some weakly entangled pairs to boost the quality of others. And because linear optics is probabilistic for full Bell projections, many groups chase deterministic middle measurements using matter-matter gates or enhanced light-matter interactions in cavities, so future repeaters can run faster than today's proof-of-principle chains. There is a famous twist that underlines the logic without adding magic. You can delay the middle Bell measurement and decide after the distant detections which pattern to test for in the middle. When you sort the data by that late choice, the far-end records line up exactly as if the entanglement had been present all along. This does not let anyone message backward in time, and it does not contradict relativity. It simply reminds you that what counts as the state shared by A and D is a statement about the whole experiment, including how you weld the middle link. What you get, in exchange for letting go of the picture of entanglement as a physical handshake, is a toolbox as practical as a router. A way to reconfigure who is entangled with whom by acting only at intermediate stations, with a public flag that certifies success, and no need for the distant parties to trust the middle's honesty about measurement settings, because the correlations themselves can be tested. If you prefer images, stop thinking of entanglement as a line between two dots, and picture instead a tapestry where patterns are defined by how threads cross. Swapping does not stretch a thread across the room. It changes the weave so distant patches now share the same motif. And if you want the one-sentence takeaway that makes you wiser after listening, keep this. Entanglement swapping shows that quantum connection is not proximity, it is architecture. By measuring the middle the right way, you can make two strangers share a secret neither could possess alone, and that quiet possibility is what turns the quantum internet from a slogan into a plan. Hardy's paradox: interaction-free interactions. You think information needs contact, that to learn where something is, you must bump into it. But Hardy's paradox asks you to accept a quieter kind of footprint, a case where two systems leave, evidence of having been in the same place, even though the very event that would have confirmed their meeting never happens. And from that absence, you're forced to conclusions that clash when you try to glue them into one classical story. Picture two identical interferometers, one guiding a particle we'll nickname electron, the other guiding its partner positron. Each a simple two-path maze that, when tuned alone, always sends its particle to a bright detector with perfect reliability and leaves the dark detector silent. That silence is the hallmark of clean interference, meaning the two paths inside are arranged so their wave-like tendencies cancel at the dark exit. Now put the devices side by side so that one path from each, the inner paths, overlaps in a tiny crossing zone. If both the electron and the positron ever occupy that overlap at the same time, they would react and vanish into other particles. An unmistakable we-met event that kills the run. When you send the pair one by one through their devices, most of the time, nothing dramatic happens. Each travels both paths in principle. Interference works its usual magic, and both bright detectors click as if the other interferometer didn't exist. But now and then, something rarer plays out. One dark detector clicks. In the single interferometer world, a dark click means interference was disturbed. Somewhere, somehow, the quiet balance between the two paths was broken. So, you infer that the other interferometer must have put a kind of block in the inner path. In Hardy's geometry, that block can only be the possibility that the partner particle might have been in the overlap. The mere chance of mutual presence is enough to spoil perfect interference and allow a dark click. Here's the paradox's sting. There are also rare cases where both dark detectors click in the same run. Each dark click, by the logic above, tells its own story. The other particle must have been in the overlap. Join the stories and you get a contradiction. If both were in the overlap, the reaction should have fired and no detectors should have clicked. If the reaction didn't fire and both dark clicks registered, how can each be so sure about the other's path? The paradox is not statistics gone wild, but reasoning on the edge of what classical language can sustain. Local inferences that are individually sensible refuse to merge into one global, contact-based narrative. To make this more than a clever riddle grounded in how labs actually test the idea, electron-positron pairs are tricky, so experimenters often use photons and replace annihilation with an exclusion rule enforced by optical interference. Two photons made indistinguishable at a beam splitter exit together from the same port rather than separately. So certain coincidences can't occur if both try to take the overlapping arms. A stand-in for they can't both be there. By carefully timing sources, matching colors, and erasing any telltale differences between the middle arms, teams reproduce the Hardy pattern, mostly bright clicks, sometimes one dark, and, at a calculable small rate, a double dark event that sanctions the contradictory inferences. No laws are violated in those runs, no energy appears from nowhere, no faster-than-light messages ride on the clicks. Yet the algebra of the setup ensures that if you insist on a single, simultaneously valid assignment of which path to both particles, you will predict that double dark should never happen, even though it does. So where does the classical picture break? One easy mistake is to treat counterfactual statements. If I had opened this box, I would have found X, as if they can be chained together across different, mutually exclusive measurement contexts. Another is to assume that properties, like was in the inner arm, exist with definite truth values, even in those runs where the experiment was tuned precisely to make such assignments undefined. Hardy's exercise forces you to confront both mistakes at once. A dark click licenses an inference about the other device only within the context of that device's own interference conditions, and trying to read both dark clicks as simultaneous. Proof of two definite, path-like facts drags you outside any single, consistent context the apparatus provides. It's tempting at this point to slip into dramatics. Quantum particles sense each other without touching, but the sober reading is more instructive. The paradox doesn't show mysterious telepathy. It shows that interaction-free information is real. The possibility of an interaction that did not occur can change what counts as evidence. The inner arms don't carry labels that detectors read. What they carry is the capacity to erase or preserve the indistinguishability of alternatives, and that capacity shapes the click pattern even in the runs where the dramatic event, annihilation, or its optical stand-in, didn't happen. The double dark run is special because each device, from its own point of view, saw interference fail, which in the single device logic points to a block in the overlap. But the two blocks cannot be asserted together without contradicting the very conditions that gave each inference meaning. In modern language, you'd say Hardy's paradox exposes contextuality. The outcomes you can sensibly ascribe depend on the full measurement context, not on a catalogue of pre-existing path facts, and trying to knit together facts from incompatible contexts leads to paradox. There's also a connection to non-locality without inequalities. Unlike Bell tests, which show quantum predictions outrun any local hidden variable model by violating a numeric bound, Hardy's setup builds a direct logical impasse. These outcomes can't happen together, versus the theory says they sometimes do, for a broad class of entangled states. That's why Hardy's argument matters. It tightens the noose on any worldview that tries to keep both locality and classical realism intact. If you want utility and not just philosophy, consider what Hardy-type ideas buy you in practice. They underpin interaction-free measurement schemes where you can detect a light-sensitive object without absorbing a photon, a theme that can be repurposed into ultra-delicate imaging techniques and into sensor designs where exposure is costly. They inform quantum communication protocols that certify the presence or honesty of a partner by the absence of certain events, which is valuable when eavesdroppers can fake positive clicks but have a harder time faking the structured silences quantum interference creates. They also sharpen your intuitions for post-selection strategies across quantum technologies. By selecting only rare runs with paradoxical-looking signatures, you can amplify tiny effects or isolate clean sub-ensembles, where you can test the limits of competing interpretations without wrecking your system. And yes, at the frontiers, people have gently probed Hardy setups with ultralight touches to map where the particle was, in an average sense, revealing patterns that look like negative presence in the overlap. You should read those results, not as claims that particles have negative mass or visit places with negative frequency, but as operational fingerprints of interference among the few histories that survive the severe filtering Hardy's geometry imposes. The human echo of all. This is as practical as it is humbling. You and I make Hardy-style mistakes whenever we chain together inferences from different contexts as if they belong to one stable ledger. If she didn't reply here, she must have read that. If this number moved there, the cause must be that. And then we're shocked to find a double dark event in life, a pair of conclusions that can't both be true in the same frame. The cure is not to stop inferring, but to respect context. To remember that evidence is shaped by the questions that could have been asked but weren't, by possibilities that quietly disciplined outcomes, even when they didn't occur. Hardy's paradox doesn't tell you that reality is a lie. It tells you that parts of reality are relational, that what happened can depend on which web of comparisons you choose to build into your apparatus and into your reasoning. When you honor that, the paradox stops being theater and becomes a method. Engineer contexts where absence is informative, learn to read structured silences, and be wary of stitching together truths that were born in different rooms. In the lab, that discipline predicts the tiny but undeniable rate of double dark clicks. In a life, it keeps you from forcing a single narrative out of incompatible clues. Either way, you leave smarter. Sometimes, the loudest fact is the thing that didn't happen. And sometimes, two such facts refuse to live in one story, because the world, at its most honest, protects consistency not by giving you more contact, but by making you choose which context you're actually in. Elitzur Vaidman bomb tester intuition. You want to tell whether a device is dangerously live without ever touching it, and the Elitzur Vaidman bomb tester gives you the audacious blueprint. Arrange things so that a single photon's mere possibility of meeting the bomb will change the pattern of what you see, letting you identify some live bombs without setting them off, which sounds like cheating until you realize you're not reading secret messages from the future. You're exploiting how quantum alternatives cooperate or stop cooperating, depending on whether they could, in principle, be told apart. Here's the intuition in plain terms. Build a light maze with two routes to a pair of detectors and feed it one photon at a time. Tune the mirrors so that when both routes are open and indistinguishable, the two ways the photon could arrive interfere like ripples that boost one detector's chance and cancel the others completely, giving you a bright port and a dark port. Now slip a suspect bomb into one route, the kind that would explode if so much as a single photon actually hit it. You've changed more than plumbing. You've changed what the world can know about the photon's path. If the photon tries, the bomb's route, there's an explosion and the run is over. If it takes the other route, you've created a telltale situation. The two alternatives are no longer on equal footing because one of them could have left a catastrophic record. So the neat cancellation that made the dark port silent is spoiled. Every so often, the photon reaches that formerly silent detector, and the click that should have been impossible becomes your proof. The bomb must be live, because only a live device would have broken the delicate cooperation between the two routes. In that lucky case, nothing absorbed the photon, nothing detonated, and yet you learned the crucial fact. That is what interaction-free means here. Not that nature forgot about interactions, but that the information rode on the possibility of an interaction that did not occur. The price is that this success is probabilistic. Some fraction of runs ends in a harmless bright click that tells you nothing, and a smaller fraction ends in an explosion, because the photon did take the booby-trapped path. But the door this opens is wide. You can, in principle, sort out a subset of truly live bombs without ever sacrificing one. The idea gets sharper once you replace the cartoon with lab reality. You do not pour in a classical beam. You send quantum-limited pulses so that one photon at a time really means one, because a bright beam would just guarantee an explosion. You make the two routes as indistinguishable as engineering allows, same length to within a tiny fraction of a wavelength, same spectra, same polarization, so that with no bomb, the dark port really is dark. You add detectors with low false alarms, so that a click at the dark port is meaningful. Then you test. With no bomb or with a dud, you see the bright-only pattern. Insert a live absorber, and, with a calculable chance, the dark detector lights up even though the absorber never fired. That no touch, yet a trace, is not a loophole in physics. It's the direct consequence of how knowledge about alternatives erases the interference that would otherwise hide a path's fingerprint. If you worry this is a parlor trick with miserable odds, here's the improvement that makes it powerful in principle. Rather than send the photon into a single 50-50 splitter, you can split it many times very gently, peeking over and over at whether the bomb route is available while almost never sending enough amplitude down that path to trigger it. This quantum interrogation idea turns the quantum Zeno effect into a safety shield. Frequent, weak checking keeps the system aligned with the safe route. The live bomb's mere availability keeps interference from perfectly cancelling the dark outcome, and your chance of a dark port success climbs toward unity, while the chance of an explosion shrinks towards zero. Experiments have demonstrated large boosts in efficiency with multi-stage interferometers, and although perfect performance is limited by loss, jitter, and imperfect components, the logic is sound. By dividing risk into many almost risk-free glances, you can learn more with less exposure than any classical scheme permits. The same logic explains what this is not. It is not faster than light messaging. The click that tells you live appears only at your detector after your local choice of setup. No distant party can force a pattern at your place. It is not retroactive editing. Once a run ends, whether by explosion or by a click, the record is fixed. Sorting results afterward is bookkeeping, not time travel. And it is not a claim that the photon took both paths and also didn't. The safe story is simply that when two alternatives are distinguishable in principle, because one would have left a trail of heat and shrapnel, their phases stop cancelling in the way that makes the dark port impossible, and you can cash in that loss of cooperation as a new kind of evidence. Why should you care beyond the novelty of diffusing fictional bombs? Because the same trick, let the possibility of damage carry information, is invaluable when your target is fragile and every absorbed particle hurts. Interaction-free imaging schemes aim to outline a light-sensitive sample while exposing it to far fewer particles than a classical camera would require. Quality assurance tests could, in principle, weed out defective but hazardous components without wasting them. And in quantum networks, related interference ideas certify the presence of a device or a path by watching for structured absences rather than fragile positive signals. There are sober hurdles. Real interferometers drift, detectors misfire. Any stray information leaking to the environment blurs the neat dark port logic, and the ultimate gains come with a cost in time, since you succeed by trading single big risks for many tiny ones. But the conceptual upgrade is permanent. You learn to read could have happened as data, to design apparatus where non-events are as eloquent as events, and to recognize that knowledge sometimes arrives not with a bang, but with a whisper from a channel you kept open, yet wisely did not use. The quiet ending is this. The bomb tester does not romanticize mystery. It teaches a discipline. Engineer indistinguishability when you want interference. Engineer distinguishability when you want information, and remember that at the quantum scale, both are tools. Use them well, and you can touch what you dare not touch, proving that in a world ruled by possibilities, sometimes the safest way to find the truth is to listen for a silence that should not have been there. Schrödinger's cat, revisited with decoherence. You've heard the morbid riddle so many times it feels like folklore, a cat sealed in a box, life or death chained to a quantum event, and yet the modern lesson slips past the punchline. The right way to revisit Schrödinger's cat is to watch how the world outside the box crawls into it, because the air, light, and walls relentlessly measure the cat long before you ever lift the lid, and that everyday leakage of information is what physicists call decoherence. Start with a clean picture you can hold in your head. A single, unstable nucleus is hooked to a Geiger counter that, if it clicks, shatters a vial and releases poison. If it doesn't, the cat naps on. In textbook fantasy, the whole system can be in a superposition, decayed and dead, plus not decayed and alive, until an observer looks. That fantasy assumes the box is perfectly isolated, a snow globe that never trades the slightest whisper with its surroundings. The reality is harsher and more helpful. Even in darkness, the cat collides with air molecules, emits body heat as infrared light, jiggles the box with tiny vibrations. The Geiger, tube, and the trigger and the vial do the same. Every one of those interactions entangles the cat plus apparatus with the environment, copying faint, telltale differences between alive and dead into a sea of particles. Those copies are what matter. In quantum terms, interference requires that the alternatives stay indistinguishable. Once the environment carries away enough clues to tell the stories apart in principle, the delicate cross terms that would let the two cat states recombine are driven to practical zero. No mystical collapse is required to explain why you never see a cat that is both purring and not. The environment has already performed a million little measurements that select robust pointer states, like well-defined positions, broken, vials, triggered counters, and they do it on timescales so short they make a blink seem geological. For macroscopic objects, the numbers are brutal. A dust grain in air can lose coherence between two nearby locations in far less than a nanosecond. A warm object radiating light decoheres its position even faster, and a living mammal, awash in warmth, moisture, and molecular traffic, is a decoherence factory. This is why interference with big things is hard but not impossible. When experimenters flew C-60 buckyball molecules through interferometers, they chilled, cleaned, and evacuated the path so the molecules wouldn't shed which-way hints. When they suspended tiny mechanical membranes or fashioned cat states of superconducting currents, they refrigerated them to a fraction of a degree above absolute zero and wrapped them in electromagnetic silence. In every success, the recipe is the same. Starve the environment of clues and coherence can live long enough to be seen. Decoherence also reframes the measurement problem in a sober light. It does not decree which outcome you will find when you finally look. It explains why, before you look, the alternatives have stopped being able to interfere and have instead become classically exclusive records that spread outward like ripples. That spreading, sometimes called quantum Darwinism, is the reason many independent observers later agree on what happened. The environment redundantly broadcasts the same macroscopic facts: vial broken, counter clicked, cat motionless. So dozens of glances at scattered photons or air molecules all point to one robust story. The miracle isn't that observation conjures reality, it's that the world's constant self-monitoring makes certain stories so redundantly imprinted that your late arrival can only confirm them. If you press the philosophy, you still face a choice of interpretation. In many worlds, decoherence is the branching mechanism that prevents branches from talking. Each outcome is real in its own non-interfering slice, and your experience rides one slice. In objective collapse ideas, decoherence is the practical prelude, and a new physical rule picks a single result for everyone. In agent-centered or relational views, decoherence tells you when it's legitimate for an observer to treat one outcome as fact, because all the uncontrolled copies have made interference impossible for that observer. There is no God's eye ledger until records are compared. But whichever story you favor, the operational lesson is identical. Open systems behave classically because the environment shreds quantum superpositions into locally stable mixtures unimaginably fast. That insight is not armchair talk, it is a design manual. Quantum engineers align with pointer states when they want stability, storing information in degrees of freedom the environment already protects, and fight pointer states when they want strangeness, shielding fragile superpositions from every eavesdropping atom. It is why quantum computers wrap their qubits in cryogenic stillness and run error correction loops that continually measure without revealing to push back against the world's curiosity. And it is why your kitchen, teeming with warm molecules and scatterers, never serves you a superposed chair. By the time you glance at it, millions of environmental witnesses have already decided which way the chair faces. So, when you hear the cat story again, resist the cartoon. The box was never the stage, the air was. The mystery was never whether consciousness flips a coin. It was how quickly a world full of tiny, honest collisions turns possibility into mutually exclusive records. And the quiet closing thought is this: you do not need to kill the magic to keep the truth. The cat thought experiment was a brilliant provocation, but its modern answer is not spooky at all. It is the steady hum of a universe that keeps tabs on itself, and in that constant accounting, macroscopic ambiguity doesn't die with a flourish. It fades, almost instantly, into the background noise of everything else. The causal inequality, indefinite order. Proven. You trust cause and effect the way you trust the steps on a staircase, one after another, supporting you because their order never changes. So the claim behind the causal inequality sounds almost impolite. If the world inside your experiment is forced to respect a single definite order of operations, then no matter how clever your gadgets are, there is a hard ceiling on how well certain coordinated tasks can be done. Cross that ceiling, and you've proved that the order itself cannot be fixed, that the steps sometimes braid instead of stack. The cleanest way to feel this is as a little game. Two labs, far enough apart that sending a message back and forth in one run is impossible, receive short inputs from a referee and must produce short outputs that jointly satisfy a rule. Think of it as a paired challenge, where sometimes Alice must help Bob guess her bit, sometimes Bob must help Alice guess his, and crucially, they don't know in advance which direction the help will be needed. If nature makes them choose a single causal direction per run, then there is a provable upper bound on their average success. In such a definite order universe, you can route the information only one way, so half the time your message is heading in the wrong direction, and the best global strategy is capped by a number strictly less than perfection. That cap is the causal inequality, a bell-like fence, but for time order rather than for local realism. Now for the audacious move. Quantum theory allows processes where the order in which one lab's operation occurs relative to the others is not a pre-existing fact of the run, but is instead placed in a superposed or otherwise indefinite relation. Under those conditions, the pair can beat the definite order cap. The proof is operational, not poetic. You don't argue about world lines or metaphysics. You wire up a device in which whether Alice's input is processed before Bob's or after Bob's is controlled by a separate quantum system, and you align things so that no single narrative, first A, then B, or first B, then A, can explain all the statistics. Feed this indefinite order box into the same guessing game, and the success rate climbs above the causal bound. That numerical jump is your certificate. Any model that insists there was a single underlying order per run cannot reproduce what you saw. So the order was not merely unknown, it was indefinite for the task that mattered. This is not the same. As the indefinite order you can certify with a causal witness, which is like an entanglement witness. It tells you your process cannot be decomposed as any mixture of fixed orders, but it doesn't by itself prove an advantage in a specific task. The causal inequality goes further. It says, here is a concrete job no fixed order resource can do beyond this limit. If you do better, you have shown indefinite order is at work for this job. The games are designed to be merciless in that way. You might imagine a counter. Isn't this just parallel, computing in disguise? No. Parallel devices still respect a single partial order of dependencies, a wiring diagram you can draw without loops. Processes that violate a causal inequality refuse to fit into any such diagram. Another reflex is to worry about time machines. If neither direction is fixed, can Alice smuggle a message to Bob's past? The rules of the game forbid that. The advantage comes not from rewriting yesterday, but from choreographing the operations so that the pieces of information each lab needs are exposed conditionally within a single run, making the overall process respond, as if time's arrows could, point both ways without allowing controllable signals to travel backward. In practice, this choreography looks like a control system, the conductor, that coherently toggles the order in which two black box transformations act on a target system. When that control remains quantum, and when the two transformations don't commute in a way that erases the effect, the joint device implements a process that no mixture of fixed orders can mimic. For some tasks, that indefiniteness buys you a mathematically provable edge over any definite order strategy. That edge is the inequality violation. Why should you care, beyond the philosophical thrill? Because order turns out to be a resource you can engineer. In communication, an indefinite ordering of two noisy channels can rescue bits that either fixed ordering would lose, raising capacities in regimes where classical intuition throws up its hands. In metrology, the same trick lets you estimate properties of transformations with fewer queries, bundling A then B and B then A into one coherent run and squeezing more information from each probe. In distributed computation, networks that deliberately refuse to impose a single global order can solve some promise problems with fewer calls to subroutines, shaving the overhead that would otherwise come from trying both sequences separately. Even security gets a foothold. Protocols can be designed so that an eavesdropper forced to pick a definite order leaves signatures that a truly indefinite order line would not. None of these miracles violate relativity or thermodynamics. They exploit the difference between a world where the wiring diagram is drawn before you press go and a world where the diagram is a controllable quantum variable inside the computation. Of course, turning the principle into practice is demanding. To witness a true inequality violation, you must close mundane loopholes, ensure the labs are space-like or otherwise shielded, so one cannot secretly feed information to the other mid-run. Certify that the control remains genuinely quantum through the whole device, and guard against sneaky classical side channels that would fake the advantage. As with Bell tests, the credibility rides on a stack of checks. Calibration that both choices of task are genuinely random from the lab's points of view, tomography or witnesses that the process isn't just a fast switch pretending to be quantum, and sanity tests showing that when you deliberately destroy the coherence in the control, the advantage collapses back below the causal bound, as it should. Each of those checks is not busy work. Together, they carve away the classical explanations until the only story left is the one you set out to test, that the experiment's success required treating which came first as an internal quantum degree of freedom. It's worth separating. One last pair of ideas that often get blurred. Indefinite causal order does not mean no cause, and violating a causal inequality does not mean anything goes. It means that the partial order of operations, the backbone that tells you who can influence whom within a run, need not be a static background. It can be state-dependent, coherently controlled, and even put into superposition, just as position or polarization can be. In that light, causal inequalities are not weird at all. They are the right kind of guardrail for a universe whose micro-laws are time-symmetric, but whose macroscopes normally force us into a single temporal lane. The reflective payoff is gentle but deep. You learn that some of our most basic seeming categories, before, after, upstream, downstream, are not axioms but choices you can encode or relax, depending on what you want a system to do. In your daily life, you experience a tame version of this when you reorganize a workflow. Tasks that seemed chained can sometimes be braided if you redesign the constraints. Information that needed 2 meetings can be folded into one if you orchestrate how and when pieces are revealed. Physics makes that metaphor literal by proving, with a violated bound, that certain jobs demand a world where order is not set in advance. It invites you to stop treating time's grammar as a fixed scaffold and start treating it as a tool. Use it linearly when that's honest and efficient. But when a problem begs for it, learn to braid. Leggett Garg inequalities. Is reality macro-real? You are certain that a coin on your desk is either heads or tails right now, even if you refuse to look, and that confidence in a single definite state is what the Leggett Garg program dares to audit with a simple but brutal question. If macroscopic objects always possess well-defined properties, and, at least in principle, we can check those properties without disturbing how they later evolve, then there are iron limits on how strongly a system's values at different times can be correlated, and those limits, the Leggett Garg inequalities, ought to hold for anything we would honestly call macro-real. Start with the intuition before the jargon. Imagine monitoring a 2-state needle at 3 or 4 moments during its life and recording how often the signs at different times match. If the needle always had a definite value whether or not you looked, and if your peaks could be made non-invasive in the ideal sense, then the web of time-separated correlations must fit together like edges of a triangle. No single edge can be too strong without breaking consistency with the others, so a particular combination of those correlations is bounded. That combination is the Leggett Garg inequality, the temporal cousin of Bell's spatial bounds. Bell tests compare 2 far-apart systems at the same time. Leggett Garg compares one system to itself at different times. Quantum mechanics predicts that a system kept coherent between looks can violate that bound, meaning the correlations are stronger than any macro-realist picture allows, because your gentle probes do not merely read a pre-written value. They participate in the story the value becomes. The catch is that you must be ruthless about a loophole that always lurks. Perhaps your measurements are just clumsy, jostling the system and faking a violation. Leggett and Garg anticipated that complaint and built in the second pillar, non-invasive, measurability. It should be possible in principle to learn the value without nudging the future. In the lab, you can only approximate that ideal, but there are disciplined strategies for doing so. One is the ideal negative result trick. You set up your apparatus so that if a detector remains silent, you still gain information. And because nothing clicked near the system, you argue that you did not disturb it. Another is to use weak measurements that extract only a whisper of information in each shot, but averaged over many runs, reveal the needed correlations while disturbing the dynamics far less than a strong projective look would. A third is to design quantum non-demolition readouts and quantum non-invasive protocols, where an ancillary meter is entangled with just the right property, so that reading the ancilla leaves the system's relevant observable unchanged for what comes next. And a pragmatic fourth is to assume stationarity, that the statistics depend only on time differences, not on the absolute start time, so that you can reconstruct the needed correlations from separate, single-pass experiments that avoid repeated pokes on the same run. When these safeguards are in place, that triangle-like bound becomes a clean target. Stay below it, and a macro-realist storyteller can still explain the data. Break it, and you have evidence against macrorealism that cannot be shrugged away as ordinary measurement back action without explicitly abandoning the non-invasive in principle hope. What does the evidence look like when you get your hands dirty? In superconducting circuits, experimenters have prepared a current or phase degree of freedom in a delicate superposition, used microwave pulses as nearly non-invasive probes, and extracted time-separated correlations that jump past the Leggett Garg ceiling. In solid-state spin systems such as nitrogen vacancy centers in diamond, carefully timed sequences of weak or ancilla-based reads produce the same pattern. In photonic platforms, weak measurements on polarization or path allow a single photon to serve as its own time series, and the reconstructed correlations defy the macro-realist bound. Even in ultra-cold atoms and nuclear spin ensembles, adapted protocols have been used to demonstrate violations while keeping a close eye on the clumsiness critique. None of these platforms claims a human-scale cat or chair violating the inequality, and you should be suspicious of headlines that suggest otherwise. What they do claim and show in repeatable numbers is that as you scale control outward from single quanta to mesoscopic devices, quantum coherence can persist long enough for time-separated correlations to exceed the macro-realist limit. The failures to violate are just as instructive. Let the environment leak information. Heat, stray light, vibrations, and the same setup sinks safely below the bound. Coarse-grain your measurements so they blur small distinctions, and the inequality settles into satisfaction again. Those boring outcomes are a feature, not a bug. They remind you that what we call classical behavior can emerge not because the underlying rules change, but because decoherence and coarse readouts enforce a mercy rule on quantum interference, nudging any realistic probe toward macro-realism's comfortable ledger. That perspective was sharpened by theorists who showed that even without an external environment, deliberately fuzzy measurements can wash out the very temporal signatures Leggett and Garg target, sharpen the readouts, and shield the system, and the violation returns. In this way, the inequalities become not only a philosophical test, but a diagnostic tool, a yardstick for how much coherence your platform retains between successive touches, and a benchmark for quantumness that complements spatial Bell tests and contextuality witnesses. Because the test is temporal, Leggett-Garg experiments also force you to tidy your language about causation. Violating the bound does not mean effects precede causes, or that you can message yourself from tomorrow. It means that the trio of assumptions the system has a definite value at all times. It's possible in principle to measure that value without disturbing future behavior, and records flow forward in a way compatible with classical induction cannot all be true for the data you collected. You can save the inequality by surrendering any one of them, and different interpretations of quantum theory choose different surrenders. A strict operationalist gives up macro-realism and keeps the rest. An objective collapse fan keeps macro-realism and drops universal non-invasiveness by adding a genuine stochastic kick when systems become macroscopic. A superdeterminist might try to weaken the independence of settings. A relational thinker reframes the values as observer relative so that non-invasive measurability in principle loses its universal bite. Whatever your taste, the inequality serves as a map of trades, making explicit which comfort you must relinquish to keep the numbers honest. Alongside these conceptual stakes sits the practical work of closing loopholes. The clumsiness loophole is the biggest. Perhaps your supposedly gentle read still perturbs the system in a way that a macro-realist would say invalidates the premise. That's why negative result designs, QND readouts, and independent invasiveness calibrations are vital. Detector inefficiency and fair sampling assumptions matter too. If you throw away many runs, you must show you haven't cherry-picked a special subset that would violate any bound you set. And just as with Bell tests, clever sanity toggles help. Deliberately degrade coherence and verify that the violation disappears. Randomize control parameters to prevent the apparatus from learning patterns. And cross-check that when you replace the quantum device with a classical surrogate, the inequality tightens back up. Why should you care beyond the thrill of watching a famous bound fall? Because Leggett Garg inequalities sit exactly at the interface where quantum engineering meets your intuition about macroscopic reality. As a technologist, you can regard a violation as proof that your device preserves the fragile phases that make quantum computation, sensing, and communication superior. As a metrologist, you can mine the same temporal correlations to squeeze better estimates out of noisy time series. As a philosopher with a soldering iron, you can use the inequality to ask not, is the world weird, but which assumption do I actually rely on when I reason about everyday objects? The quiet conclusion after all the careful apparatus and statistical bookkeeping is not that tables are secretly in two states or that coins flip themselves when you look away. It is that macro-realism is an emergent convenience enforced by environments and coarse observations, and that when we peel those supports away, even for surprisingly large and complex systems, the temporal fingerprints of quantumness are still there, measurable and useful. That realization doesn't make your desk any less solid. It makes your picture of solidity more honest, a stability born of incessant monitoring and limited resolution, not a law of nature written in stone. And it leaves you with a disciplined habit of mind. When you think about what is the system really like between now and later, be clear about which assumptions you are importing. Then build the experiment that tests them, accept the bound if you must, and celebrate the violation when you earn it. Because either result teaches you how reality chooses to look classical, at our scale without ever ceasing to be quantum underneath. Page Wootters. Time from entanglement alone. Freeze the whole cosmos in your mind, not as a slow motion film, but as a single, perfectly still photograph that somehow contains the choreography of everything. And you've touched the odd starting point of the Page Wootter cider. What if time is not a universal river that flows for all things at once, but a pattern you read off correlations inside a timeless whole, so that change appears only to observers who use part of the universe as a clock for the rest? The motivation is real, not mystical. When you try to quantize gravity, the master equation that's supposed to generate motion can, in certain formulations, insist that the state of the universe does not evolve at all, as if reality were a solved crossword, with no empty squares. Page and Wootters ask you to stop expecting motion at the top level and to look instead for conditional motion. Split the world in imagination into two parts, a clock and a system. Prepare a joint state where the two are strongly entangled so that specific readings of the clock are tightly paired with specific states of the system, and then adopt the humble stance of an internal observer who only ever has access to the clock's hand and whatever they are studying. For that observer, the statistics of the system conditioned on the clock reading behave exactly like ordinary evolution in time, step by step, even though an imaginary super-observer with access to the entire composite all at once would see no global change. The trick is not sleight of hand, but careful bookkeeping about what questions are legitimate to ask. If the total closed universe sits in a special, stationary state, one that does not march forward under the big generator of motion, then any impression of flow must come from how parts relate. By designing those relations so that the clock's distinct ticks are correlated with an ordered family of system states, you turn entanglement into a calendar, and the Schrödinger-like story you recover for the system is not an extra postulate, but the internal narrative that emerges when you filter on the clock's successive readings. To carry this without equations, picture a long mural painted as a series of vignettes. Nothing on the wall moves, but if you decide that the leftmost strip is a clock hand that turns from pale to dark in finely graded steps, and you notice that each shade of that strip coincides with a consistent scene in the rest of the mural, then walking along the wall and checking shade versus scene lets you recover a sense of before and after. The mural is fixed, but your relational rule converts it into a story. Now translate the metaphor into hardware. In the lab, you can use one quantum degree of freedom as the clock and another as the system, then entangle them so that particular clock readings line up with particular system states. When you later slice the data by clock value, the system's conditional statistics unfold just as if an external stopwatch were running. Experiments have demonstrated this logic with entangled photons, nuclear spins, and superconducting circuits. Globally, the joint state is prepared to be as static as engineering allows. Locally, once you adopt a clock, the other part evolves, and if you choose a different internal clock, you can rewrite the same unmoving whole into a different but self-consistent movie. None of this licenses science fiction. You cannot halt aging by throwing away the clock, or make yesterday return by changing which part you label time. The equivalence with standard physics remains, because the predictions for any actual measurement are the same once you specify what you're using as a clock and how you read it. The value of the page Wootters move is clarity. It teaches you that specifying time is the same kind of physical act as specifying a ruler. You pick a subsystem with regularly spaced, reliably distinguishable ticks. You ensure that it interacts with the rest in a way that does not scramble those ticks too quickly. And then all the familiar machinery of dynamics reappears relative to that choice. Seen this way, the requirements for a good clock become concrete. The ticks must be nearly orthogonal so you can tell them apart. The clock must couple weakly enough to the system that it does not backfire and smear its own reading. And the clock's unavoidable fuzziness sets a flaw on how sharply the system's evolution can be resolved, which is why every real clock drifts and why perfect time is a fiction useful in equations but not in instruments. The framework also reframes the arrow you feel from past to future. Page Wootters by itself gives you order, not direction. To get an arrow, you still need low entropy boundary conditions so that correlations between the clock and the system, and between the system and the surrounding world, accumulate in one temporal sense and not the other, creating records and memories that point the way we experience. In that light, time from entanglement and time's arrow from thermodynamics are partners, not rivals. Entanglement supplies the scaffold that orders snapshots, while a universe rich in record-making gives those snapshots a gradient from simple to structured. Perhaps the most unsettling but fruitful consequence is a change in how you phrase certain questions. Asking, "What is the system like at a time?" becomes shorthand for, "What is the system like when the chosen clock reads this value?" A tiny shift in words that avoids paradoxes about a global now and that fits better with relativity's lesson that different observers slice space-time differently. And far from being a mere parlor trick, the relational view is already a design principle. In quantum control and sensing, one often elevates an ancilla to the role of a clock and engineers dynamics so that the thing you care about is reconstructed from correlations with that ancilla. In distributed quantum networks, synchronizing distant nodes boils down to establishing shared entanglement that ties their local clocks together. Even in quantum gravity proposals, where traditional time parameters misbehave, the page Wootters, spirit, solve the whole, then recover motion by conditioning, offers a route to meaningful predictions. The closing comfort is quiet, but sturdy. Your kitchen clock is not in danger. Standard timekeeping works because quartz, atoms, and lasers make excellent approximate clocks whose ticks correlate neatly with the rest of your world. Page and Wootters simply show that, underneath, the universe doesn't need a cosmic metronome to make sense. It needs relationships rich enough that parts can serve as references for other parts, and when they do, the still photograph gains a storyline, not because something outside pressed play, but because play was hidden in the picture all along, waiting for you to learn how to read it. Time crystals. Order without flowing time. You already know how matter can lock itself into a repeating pattern in space. Salt, snowflakes, the ridges on a seashell. So here's a gentler but stranger question to hold. Can a many-body system lock into a repeating pattern in time not because you keep pushing it in that rhythm, but because its own internal rules make a different rhythm inevitable? As if order could live a long time rather than just across space. That, carefully stated, is the realm of time crystals. Phases of matter whose collective motion breaks a time translation symmetry in a way that is both predictable and surprisingly stubborn. Begin with what they are not. They are not perpetual motion, machines humming forever in isolation, and they are not gizmos that let you mine free energy or rewind history. A time crystal needs a periodic nudge from the outside world, like a gentle drumbeat, yet it answers back at its own beat, most famously at half the drive's rate, no matter how you try to push it slightly faster or slower. That locked, subharmonic response is the signature. Imagine tapping a system once per second and watching it answer every 2 seconds again and again without drifting. You can detune the tap a little and the system still answers on twos, and you can add moderate noise and the cadence persists. Ordinary oscillators can also respond at new frequencies, but they do so because you tune them just so. A time crystal's cadence is spontaneous and rigid, emerging from many body interactions that refuse to let the drive's rhythm be the last word. Why is a periodic push allowed at all if we're talking about symmetry breaking? Because the underlying symmetry is discrete time translation, the invariance of the setup under shifts by one drive period. So when the system organizes itself to repeat only every 2 periods, or 3, or more, it has truly broken the symmetry of the problem you gave it. In the earliest theoretical proposals, this kind of order was declared impossible at equilibrium by sharp no-go theorems. A system in its true ground state cannot oscillate forever without input. The escape hatch is to leave equilibrium and use Floquet driving. You strobe the system in time, and you keep it from absorbing energy until it heats to mush by leveraging either many-body localization, disorder, and interactions combined to trap excitations so they do not spread, or a pre-thermal regime. The drive is so fast relative to the natural interactions that heating is exponentially slow for a long, useful stretch. In those protected conditions, the many-body state can settle into a time crystalline phase where the whole ensemble flips or rephases in synchrony at a multiple of the drive period with long-range temporal order, meaning distant parts of the system stay in step over many cycles, just as atoms in a spatial crystal stay in register over long distances. Laboratory realizations turned this from a metaphor into data. Chains of trapped ions were pulsed with alternating kicks that mimicked an Ising interaction and a global spin rotation. Despite imperfections, the chain answered at twice the drive period for hundreds of cycles, its subharmonic peak staying, narrow even when the pulse strength wandered. In Diamond, nitrogen vacancy spins, buried in a disordered lattice, showed the same rigidity under microwave driving. The response peak sat stubbornly at the subharmonic, rather than sliding with the knob, and the correlation time ballooned far past that of a simple driven oscillator. Superconducting qubit arrays and NMR-style ensembles have joined the list, each platform emphasizing 2 diagnostics that separate true time crystals from mere ringing. Robustness, the subharmonic peak does not track small detunings of the drive, and collectivity, the order involves many degrees of freedom and survives local pokes rather than being the quirk of a single resonant element. At an intuitive level, interactions are doing the heavy lifting. They let the system choose a collective phase of its cycle and defend it, much as interactions in a spatial crystal fix an orientation and defend it against moderate bumps. The moment you weaken those interactions or let the environment swallow phase information, the order melts. The subharmonic peak broadens, drifts, and dies, and the system slides back toward a featureless, heated state. Exactly what the no-go arguments warned would happen if you lose the special protections. This precision about what makes a time crystal real also cleans up common confusions. Ordinary devices can produce period-doubled signals through parametric resonance, but there the period is set by a fine-tuned instability and shifts when you adjust control knobs. Time crystal signals don't follow your knob once the phase is formed. Ordinary coherence can also yield long oscillations that only a simulator loves. A time crystal shows phase locking that resists slow drift and temporal long-range order visible in correlations measured stroboscopically over many sites and many cycles. And no, none of this violates thermodynamics. The drive provides energy, and any practical setup will eventually heat. The achievement is to carve out an extended plateau where heating is bottlenecked and ordered motion is stabilized. Not forever, but long enough to be measured, controlled, and used. Why care beyond? The headline? Because time crystalline order is a design principle for quantum technology. In sensing, a temporally ordered state can act like a self-referenced metronome, filtering noise that tries to smear your phase while amplifying signals that respect the cadence. In memory and computation, the rigidity of the subharmonic response offers a dynamical way to fight drift, suggesting error-protected encodings that are stabilized not by sitting still, but by marching in step. In materials engineering, the very idea of spatio-temporal phases, structures that repeat both in space and in stroboscopic time, opens a catalogue of behaviors unavailable at equilibrium, from protected edge dynamics that only appear once per several drive cycles to quasi-crystalline patterns in time when you mix incommensurate drives. There are sober limits alongside these hopes. Disorder helps by localizing, but too much disorder kills coherence. Pre-thermal plateaus can be long, but not infinite, and scaling from dozens to millions of constituents without losing protection remains a steep hill. Still, the conceptual payoff is immediate. Space taught you that perfect homogeneity is not the only honest ground for physics. Broken symmetries create new laws within their phases. Phonons in crystals, magnets with domains, superfluids with quantized vortices. Time, under a drive, joins that list. When a many-body system chooses to answer on twos instead of ones and defends that choice, it has written a new rule you can exploit, and there is a quiet, human echo in that rule. You don't experience life as an ideal, continuous flow. You live by rhythms, heartbeats, steps, seasons that persist even when the world is noisy and the schedule slips. A time crystal does not make time stop or reverse. It shows you that order can live in time itself, sustained not by an external conductor, but by the way parts of a system hold one another to a shared cadence. Learn to recognize the conditions that let that cadence form: periodic prompting, interactions that knit, protections against indiscriminate heating, and you gain both a clear picture of a once controversial idea and a new habit of thought. Sometimes the most stable thing you can build is not a stillness, but a beat. Cheshire Cat. Property here, object there. You've seen smiles that seem to float in a room after their owner has stepped away, and the quantum Cheshire Cat invites you to test a version of that feeling under strict laboratory rules. Can a particle take one route while a property you normally treat as part of it, its grin, say polarization or spin, shows up along another, so that where the thing is and where the thing points come apart in a way no classical story can? Make sense of, yet no physical law is bent or broken. Begin gently with the stage. A single particle is sent through a two-path interferometer tuned so that when undisturbed, the alternatives are perfectly indistinguishable and recombine into a predictable pattern at the outputs. You prepare the particle with a known internal orientation. For light, a polarization. For neutrons, a spin. And you arrange a final filter at the exit that keeps only those runs ending in a particular detector click. This selection is public and honest, not sleight of hand, and it creates a well-defined sub-ensemble you agree to analyze. Now the trick is to probe softly inside the arms without ruining the recombination. Instead of slamming the system with a decisive witch path check, you insert tiny path-specific feelers, minute phase shifters, weakly coupled birefringent, plates, or magnetic fields so gentle that any single pass hardly tells you anything. Yet over many trials, these feeble taps nudge a meter just enough that their averages become meaningful. When you compute those averages only for the runs that pass the final filter, a striking pattern can emerge. The gentle path meters say, in effect, the particle's presence was primarily in the left arm, while equally gentle meters that respond to the internal orientation, little polarization rotators or spin flippers placed in the arms, report that the orientation effect appears mainly in the right arm. In the cartoon language that gave the effect its name, the cat walked left while the smile drifted right. Seen through classical eyes that treat properties as tags glued to a bead, this looks impossible. Seen through quantum bookkeeping that respects how you prepared and finally filtered the system, it is a precise statement about conditional influence. The weak nudges reveal where, within the particular sub-ensemble you defined by the exit click, the particle's presence and its disposition left their faint fingerprints. Important guardrails keep the magic honest. If you crank any probe up to a strong one-shot measurement, the effect evaporates because the probe itself forces a definite path and destroys the delicate recombination that makes the averages so odd. If you skip post-selection, the quirky separation also dissolves into the ordinary interference pattern, and in no case can you harvest the setup to send a message from one arm to the other or faster than light, because the informative pattern appears only after you combine the gentle meter readings with the list of which exits clicked. Laboratory versions make this concrete across platforms. With neutrons, interferometers have shown that a weak magnetic rotation placed on one arm can shift spin-sensitive readings even when a separate, even gentler presence probe points to the other path. With photons, teams have used polarization rotators and path-marked phase tweaks to show the same directional split, the orientation living where the particle's presence meter stays quiet. And in each case, the signatures fade exactly, as theory says, when you introduce loss, decoherence, or probes that are too eager. You should also hear the sober debate these experiments triggered, because it clarifies what is and is not being claimed. No serious account says a property literally peeled off the particle and traveled alone like a ghost. Rather, the weak, path-resolved averages you extract within the selected sub-ensemble can behave as if presence and orientation have been dislocated, and that "as if" is not a metaphor, but an operational statement about how tiny, localized, interactions add up when you condition on both the beginning and the end of the run. Critics have pointed out that certain interpretations of the same data in terms of straightforward interference and meter back action can reproduce the observed shifts without invoking a roaming smile. Supporters reply that the dislocation language is just a compact way to describe those very interference patterns in the language of where a probe would have mattered. The upshot for you, as a learner rather than a partisan, is that the Cheshire Cat effect is a clean exercise in contextuality. Which statements are sensible depends on the entire measurement context, the preparation, the gentle probes, and the post-selection, and trying to promote the path and the property to context-free facts leads to contradictions that the data refuse to honor. This seemingly whimsical scenario carries real uses. In sensing, you can place the gentlest, property-sensitive element only where the smile is most detectable, and keep delicate, loss-inducing hardware away from where the particle's presence would be most harmed, effectively routing disturbance and information to different places. In metrology, weak path-specific tweaks let you extract gradients of a field encoded in orientation without sacrificing the flux of particles that encodes presence. And in quantum control, the same logic generalizes. By shaping pre- and post-selection, and by choosing carefully what you probe and where, you can steer which parts of a device feel back action and which parts deliver signal, a separation of duties that classical designs rarely allow. If the idea still feels slippery, trade the cat for a human picture that doesn't cheat. When you recall a conversation, where you were and what mood you carried can have different footprints. Your body in one room, your attention partly elsewhere, and yet both left traces that later evidence can recover if conditioned on the right endpoint. Nothing metaphysical happened, but the pattern of correlations lets you talk as if presence and tone briefly parted ways. The quantum Cheshire Cat turns that soft introspection into a sharply testable statement. Prepare with care, listen lightly along the routes, keep only the endings that match, and you will find that property here, object there is not a fairy tale, but a disciplined way of reading how the world lets different questions tug information from different places. And the gentle closing thought you can carry out of the lab is this: reality at small scales does not always give you one box to hold what it is, and another to hold how it points. Sometimes, if you ask with enough finesse, those answers live on different shelves, and learning to read them apart doesn't make the world less whole. It makes your attention more precise, and your respect for how questions shape answers a little deeper. 3-box. Paradox. Where's the particle, really? Imagine you promise to open exactly one lid, and only once, and someone claims they can arrange things so that if you lift the lid of box A, you will certainly find the particle. Yet if instead you lift the lid of box B, you will also certainly find the particle. While box C seems to carry whatever leftover bookkeeping the universe needs to keep the totals honest. This is the unsettling heart of the 3-box paradox. And your task is not to swallow contradiction, but to learn what the claim actually measures and why your everyday grammar for where things are bends under the conditions of the test. Start by setting the stage in steps you can picture without equations. You prepare a single qutrit particle spread across 3 boxes, A, B, and C, in a carefully chosen superposition. Later, you only keep those runs in which a final check, a post-selection, clicks in a specific way. Think of it as a quality filter that says, analyze only the trials that end with this signature. Between preparation and that final sieve, you give yourself the chance to peek into one box with a decisive look, or to graze all 3 with feather-light touches that hardly disturb anything. The odd promise concerns what you'll infer inside that middle window. If you choose a strong 1-box check and open A, the design ensures that in those rare runs that will later pass the final filter, A always contains the particle. Choose B instead, and, in the sub-ensemble you later keep, B always contains it. Crucially, you must not open both, because the very act of doing so derails the delicate conditions required for the final sieve to accept the run. So far, this is only surprising. The deeper twist arrives when you switch to soft probes that couple so gently to each box that any single run tells you almost nothing. But an average over many accepted runs reveals a stable tendency. The tiny presence meters, assigned to A and B, each report the same positive full-strength nudge you would expect from an actually occupied box, while the meter in C reports a negative nudge of equal size but opposite direction, so that A plus B minus C sums to 1, the correct inventory for a single particle. Read naively, this looks impossible. How can a particle be fully in A and fully in B while not overcounting? Read properly, you realize you are not measuring a classical is, but a conditional influence within the narrow slice of trials singled out by the final check. A gentle tap placed in A would have shifted your meter exactly as if the particle had been there. The same is true for B, and the negative response from C is the operational signal that interference among the allowed pathways make the influence of C cancel the double counting, restoring a sensible total. That is the entire trick, and it is as physical as an accelerometer. The sign of a weak nudge is the direction the meter deflects, not a claim that negative marbles exist. To keep your footing, you must separate 3 ideas that our language blurs. First, context. The statements, you would have found it in A, and you would have found it in B, live in different measurement contexts, because opening A would have blocked the route that leads to certainty in B, and vice versa. There is no single run in which both counterfactuals can be true. Second, conditioning. All these claims refer only to the sub-ensemble that actually passes the final sieve. If you ignore that filter and average over everything, the paradox evaporates into an ordinary spread of probabilities. Third, strength of touch. A strong look and a soft glance answer different questions. The strong look produces a definite location in that run and destroys the interference that underwrites the odd averages. The soft glance samples where a small, local interaction would have mattered given the start and the end you have fixed. With those guardrails in place, the paradox becomes a method, not a mystery. In photonic labs, the 3 boxes are often 3 spatial modes or time bins. A state preparation stage fans a single photon across them. A later interferometer implements the final sieve. Inside the window between, Experimenters insert minuscule prisms, phase plates, or polarization twists in one path at a time, and watch a meter downstream accumulate tiny shifts only in the trials that pass the sieve. The result is the pattern above: full-strength positive effects attributed separately to A and B, and a compensating negative from C, mapping exactly onto the designed preparation and post-selection. Similar protocols have been run with trapped atoms and superconducting circuits where three internal levels play the role of the boxes. There, microwave nudges or magnetic taps replace tiny optical elements, and again, the conditioned averages come out with the same double positive plus negative structure. None of these demonstrations lets you message backward in time or signal between boxes. The oddities appear only in analysis after you've kept the runs that fit the prearranged finale, and no single detection ever shows two boxes lighting up at once. The value of the exercise is what it forces you to unlearn. In daily life, you treat properties like presence as pre-written facts that you merely reveal, and you treat counterfactuals as if they can be spliced together from incompatible what-if branches without penalty. The three-box game shows you that when interference is part of the physics, both habits fail. Where is the particle really? Becomes a question about which experiment you're actually doing, which box you open, how softly you touch, and which endings you are prepared to keep. And the honest answer can be, in this context, a gentle intervention in A behaves as if it were fully there. In that other context, a gentle intervention in B behaves as if it were fully there. And in the balanced view that samples all three at once, the negative influence of C is exactly the footprint that reconciles both stories with the one-particle ledger. This is not a loophole or a magician's patter. It is a disciplined way to read how correlations laid down at the start and demanded at the end shape what counts as a sensible middle. If you want to do something with the insight rather than just admire it, notice the engineering lesson hiding in plain sight. By choosing your pre- and post-selection and by distributing gentle probes with care, you can route back action away from the channels that carry your precious signal and into sacrificial ones that carry the compensating negative, extracting information that a blunt probe would squash. In precision sensing, that means placing the lightest touch where the conditioned influence is largest and letting the negative box soak up the cancellation that keeps totals consistent. In calibration of delicate devices, it means using tailored weak nudges to map how different subsystems contribute without ever forcing a destructive read. The soft human closing echoes the physics without borrowing its jargon. You often ask, where was I really? About moments divided among options, different rooms, roles, moods, and the honest answer depends on which later commitment you choose and how you probe the memory. You can find yourself fully in more than one place relative to different questions, and another part of your life may carry a negative to keep the account from inflating. The three-box paradox doesn't make truth optional. It makes your questions precise. You leave it not with a broken world, but with a better tool. When interference and conditioning matter, treat where as a relation, not a tag, and let the data teach you how influences add, cancel, and, only when you keep the right endings, reveal where the particle and your attention really counted. Quantum pigeons. Too many birds, too few holes. You grew up with a counting rule so sturdy, it felt like common sense wearing a badge. Put 3 pigeons into 2 holes, and at least 2 must share a hole. And the quantum pigeon story is the polite but firm request to check that badge at the lab door, because there are carefully staged situations in which 3 microscopic birds travel through 2 holes. And yet every test you're allowed to make about pairs says they never shared a hole, a conclusion that is not a cheat but a lesson about how quantum questions carve reality. First, the classical rule. It assumes each bird has a definite roost at all times, whether anyone looks or not, so when you tally who sits where, you can paste the results together into one consistent seating chart. Now replace birds with identical quantum particles and holes with 2 roots in a small interferometer, and set the scene in 3 acts. Act 1. Preparation. You launch each particle in a way that treats left and right routes symmetrically, so if you did nothing else, the 3 would spread like fog across both paths. Act 2. Pair tests. You engineer tiny, non-destructive interactions that fire only when 2 particular particles happen to choose the same route. In optics, this might be a delicate element that imparts a telltale phase shift if 2 photons co-occupy a path in spins. It might be a conditional kick that appears only when 2 qubits land in the same box. Crucially, these tests are so gentle that they don't smash the fog into definite pellets. They merely plant weak, pair-specific signatures you can later read out. Act 3. Post-selection. At the end, you perform a collective check on all 3 and keep only those runs that match a particular, pre-announced pattern. Think of it as a referee's whistle saying, "Analyze these, discard the rest." When you now go back and examine the pair tests for the kept runs, you find silence for every pair. The A with B test shows no same box signature, the B with C test shows none, and A with C shows none as well. If all 3 pairwise checks say, "We were never in the same hole," you are tempted to protest that the counting rule has been violated. But look carefully at what you actually established. You did not assign each particle a fixed seat. You read out pairwise correlations within a sub-ensemble defined by a future condition. And those correlations can perfectly well say no 2 together without implying a single classical seating chart exists for that sub-ensemble. The classical rule fails here because one of its quiet premises, that your birds carry hole labels independent of how you look, no longer applies. The quantum setup makes "who shared a hole" a context-dependent statement, and your allowed context, the one that includes the referee's whistle at the end, is precisely the one where pairwise sharing is filtered away. This is not wordplay, and labs have made it tangible. In photonic versions, 3 single photons traverse 2 paths. Special beam splitters and phase shifters are arranged so that if any chosen pair meets in the same arm, a minute interference mark is stamped onto their joint record. At the exit, a global interferometer keeps only those triads that produce a specific set of detector clicks. Analyzing only those triads, researchers see the paired marks vanish across all 3 pairs. Even though, had they dropped the referee's filter, such pair marks would pepper the data. Matter wave and solid-state platforms mimic the same logic, with controlled interactions that fire only for same-hole events. And again, the kept sub-ensemble shows pair silence everywhere you check. What about the obvious counter move? Open the boxes strongly and look. If you do that, you destroy the very interference that makes the pair silence possible, and the effect disappears. You are asking a different question that the system cannot answer without changing. And what about the suspicion of retrocausality or faster-than-light shenanigans? There is none. Your end-of-line filter doesn't send messages into the past. It culls a subset after the fact, and the odd pattern appears only in that bookkeeping. The hard point, the one worth learning, is that quantum mechanics lets constraints reshape which joint statements are even meaningful. The referee's whistle is a constraint that selects runs where the 3 foggy birds reassemble into an exquisitely balanced pattern. In that pattern, the tests that would have detected pair sharing are exactly the ones you have engineered to cancel. So of course they read no if you think this means you have smuggled 3 birds through 2 holes with nobody doubling up. You are importing a notion, global, non-contextual seats, that the experiment never licensed. The payoff for accepting this discipline is practical, as well as philosophical. In crowded quantum hardware, pairwise crosstalk is a constant menace. By shaping how you prepare many-body states and how you filter acceptable outcomes, you can engineer operating regimes in which unwanted pair interactions are suppressed without freezing the whole system. In sensing networks, you can design protocols where a useful signal couples primarily to triplet or higher-order structures while all pair channels are, by construction, dark. So background pair noise vanishes in the very sub-ensemble you care to read. And in error diagnostics, the same too many birds, too few holes logic becomes a map. Place gentle monitors on the pair channels. Pick a collective end condition, and a vanishing trio of pair signals certifies that your device stayed in the delicate correlation pattern it was supposed to maintain. The quiet human echo, if you want one, is modest. How often do you force a single seating chart onto situations arranged under incompatible constraints, demanding one tidy story from data gathered for different ends, and then stumble over contradictions that were baked into your framing? The quantum pigeons teach you to separate how many from how, to ask only those pair questions your context allows, and to accept that sometimes the fairest description of a crowd comes not from finding fixed seats for everyone, but from reading which pairs never sat together in the slice of the evening you chose to keep. Non-local boxes, beyond quantum, still no signaling. You've learned to live with a strange compromise. Quantum theory lets distant things share patterns that no local story can reproduce, yet it never lets those patterns carry a message. And non-local boxes are the thought experiment that asks you to push that compromise to its limit. Imagine a black box shared by you and a partner far away that, on each use, gives each of you a yes. No answer, while you each choose one of two questions to ask, and the answers are coordinated in a way stronger than anything quantum mechanics allows, but still arranged so that your own stream of answers looks perfectly random no matter what your partner asks, so you cannot signal. This beyond quantum yet no signaling object is often called a Popescu-Rohrlich, or PR box, and it works like this in words, not symbols. Whenever either of you chooses your first question while the other chooses either question, the two answers always match. But on the special occasions when you both choose your second question, the answers always disagree. If you play the usual bell game that judges how correlated distant answers can be, classical physics caps your score because it demands a single hidden seating chart for every possible pair of questions, and quantum physics lets you push higher by exploiting entanglement but still stop short of perfection. The box, though, hits perfection every time while keeping each side's local answers stubbornly patternless, so you never get a dial for faster-than-light chat. That is the first lesson. Non-locality and signaling are not the same thing. The prohibition on messaging is a constraint on marginals, what you see when you ignore the other side, and it can be satisfied even when the joint coordination is wild. The second lesson is that such a device would be a computational superpower. If you and your partner had many copies of this box, almost any distributed task that normally needs lots of communication would shrink. You could solve long, logical puzzles with hardly any talk. You could compute joint properties of your private data with just a single bit exchanged, and entire classes of problems that seem to demand bandwidth would collapse to a whisper. That fantasy has teeth, because theorists showed that if nature allowed PR-level non-locality while keeping no signaling, then communication complexity would be trivial for broad families of tasks. Randomness certification would be absolute, device-independent. Crypto would be both powerful and fragile, and the familiar balance between information and disturbance would tilt in ways that feel unphysical. Confronted with that, you learn a deeper point. Quantum mechanics is not as non-local as possible under no signaling. There exists a no-signaling polytope of all correlations that respect the ban on messaging. Inside, it sits a rounder, narrower region of correlations that real quantum states can generate. And inside that sits the yet smaller region, achievable by classical shared randomness. The PR box sits at a sharp corner of the outer shape. It obeys the letter of no signaling, but ignores many softer constraints that quantum theory seems to honor. What are those softer constraints? Different research programs propose different answers in plain language. Information causality says that if you send me a limited number of classical bits, then the total information I can gain about your long data set cannot exceed those bits, plus what our shared resource intrinsically provides. PR-type boxes violate this, letting me learn more than I paid for. Non-trivial communication complexity demands that some problems should always need genuine talk. PR boxes would make almost everything cheap, so the world would be computationally too easy. Macroscopic locality says that if you coarse-grain a huge number of microscopic trials, the resulting averages should behave classically. PR boxes can wreck that expectation. Local orthogonality insists that outcomes that rule each other out locally cannot all be jointly likely once many parties get involved. PR-style resources can overstuff those probabilities. Each principle slices away part of the no-signaling polytope, and their intersection hugs the quantum set, which is our hint that quantum mechanics is not defined only by equations in a vacuum, but by deep information theoretic norms about what counts as a fair trade between what's learned and what's disturbed. That perspective gives you a gentle way to read the famous quantum limit on Bell violations. Not as a frustrating shortfall, but as a safety line that keeps the universe from a world where correlations would trivialize communication, swamp thermodynamics, with super-strong steering of statistics, and erase the delicate balance that lets measurement be both revealing and costly. In practice, non-local boxes live on whiteboards, not in labs. Real experiments demonstrate non-locality by violating Bell bounds up to the quantum limit, never beyond it, and always with awkward realities in the mix, loss, noise, finite statistics, that must be tamed to close the usual loopholes. Yet the box is not idle fiction. It guides design in device-independent protocols, where you refuse to trust the internals of your gadgets and rely only on the pattern of their correlations. It calibrates your expectations when building networks that share entanglement across many nodes, and it disciplines your language about cause and influence, reminding you that structure in joint data need not carry a message path. The philosophical echo is gentle rather than grand. You learn that there are different kinds of impossibility, hard bands like no signaling, and softer structural preferences like information causality, and that quantum theory, far from being a maximal enemy of locality, is the particular compromise that respects both. So when you hear beyond quantum, resist the urge to plug your ears or to chase magic. Instead, let the PR box stand as a lighthouse past the reef, marking a coastline. The real ocean does not cross. You can sail close, harnessing entanglement to outrun classical ships, proving non-locality without a cable. But you do not want to leave the bay where messages stay tame, where computation still costs something, and where learning from the world never becomes a free lunch. GHZ states, deterministic weirdness sans inequalities. You've heard that quantum strangeness usually hides behind averages and inequalities, teasing you with statistics that only slowly betray a mismatch with classical expectations. So let's invite a louder witness. The GHZ state, where three distant systems behave in a way that forces an immediate yes or no clash, with any picture in which each piece carried its own pre-written answers. A demonstration so clean that no inequality is needed, and no long data run is required. You can see the contradiction in principle from a single, perfectly executed round. Imagine three labs, yours and two friends, far apart, each holding a two-level system prepared together in a special, phase-locked entangled state whose simplest cartoon is all three up added to all three down. Before you start, you all agree on a tiny menu of tests. In each lab, you will choose one of two complementary questions about your local system's orientation. Roughly, spin along one sideways direction, or spin along a perpendicular, sideways direction, and you will record a result that can only be plus or minus. Quantum theory makes four remarkable, deterministic promises for this shared state. First, if all three of you ask the same sideways question, the product of your three plus-minus answers is guaranteed to be negative. Second through fourth, if exactly one of you asks the first question and the other two ask the perpendicular one, the product is guaranteed to be positive. No ifs, no probabilities. That is already enough to corner any classical storyteller. A local realist wants to say that each particle carried a hidden card listing the answers it would give to either question, because your choice in one lab should not rewrite the card in a distant lab, but try to write such cards while honoring the four quantum promises, and you get stuck. When you multiply the three mixed cases together, you are forced to predict a positive product for the all-same question case. while the actual GHZ state demands a negative one. There is no wiggle room, no appeal to detector inefficiency in the logic itself, no refuge in, well, the bound was only statistical. You are looking at an all-or-nothing contradiction. This is why GHZ is called deterministic weirdness. It replaces the gentle slope of a Bell inequality with a brick wall. The lesson is not that fate flips mid-air depending on your whim, but that the idea of pre-existing local answers that don't care which combination of complementary questions will be asked elsewhere, cannot be made consistent with the perfect correlations this state exhibits. To feel the mechanics without drowning in symbols, think in terms of symmetries and checks. The GHZ state is stabilized, that is, kept fixed, by certain joint flips of all three systems, so the state is arranged to answer coherently when you probe particular patterns of sideways orientations. That coherence means there are collective facts about the trio that are sharper than any single local fact. You can know, with certainty, the joint parity of three answers for one pattern of questions, while each individual answer remains unpredictable when viewed alone. Classically, knowing the product of three signs is just a shortcut for knowing the three signs separately. Here, the product is an autonomous fact that does not reduce to pre-written locals. The payoff is practical as well as philosophical, because the GHZ contradictions are deterministic. They provide device-independent ways to certify that three-way entanglement is really present, even if you decline to trust the internal workings of the boxes in each lab. Observe the four parity relations, and you have witnessed a resource no classical setup can fake. That resource powers protocols that truly need three parties at once. In quantum secret sharing, for example, you encode a secret so that no single lab and no unauthorized pair can recover it. Only when all three parity relations are tapped, in cooperation, does the secret reappear. In error correction, the same triple symmetry underlies the simplest code that can correct a single bit flip by measuring joint parities that reveal where a fault occurred without exposing the protected data itself. In measurement-based computation, GHZ-like and larger graph states provide the substrate on which single-site measurements drive multi-qubit logic. The same rigid parity structure that makes the GHZ paradox sing is what makes these states programmable substrates rather than delicate curiosities. And in multi-sensor quantum metrology, entangling three probes into a GHZ state lets you estimate a common phase with enhanced sensitivity, because the phase shift is written onto a global parity that tiny, local jitters average away. Turning from principle to practice, you'll want to know whether this is only a chalkboard fable. Experiments with photons have produced 3- and 4-photon GHZ states by letting independent emissions interfere until the all up plus all down pattern emerges, and then have tested the parity promises with rapid, randomly chosen measurement settings at separated stations. Trapped ions have prepared GHZ states through shared vibrational modes, reading out the joint parities with nearly perfect visibility. Superconducting processors now create GHZ states of dozens of qubits on a chip and verify their stabilizers, with repeated rounds that highlight the same contradictions at scale. The experimental complications, loss, crosstalk, imperfect alignment, do not change the logic. They just add noise that turns the sharp contradiction into a percentage game in practice. But even there, the GHZ structure gives you leverage. You can design self-testing routines where certain observed patterns of perfect or near-perfect parities guarantee, up to well-understood twists, that the underlying state must be close to GHZ, and you can use entanglement witnesses tailored to trip only on genuine three-way correlations, not on pairs cleverly masked by randomness. The deeper conceptual payoff is what GHZ does to your idea of realism, locality, and context. Bell's Inequalities already told you that no mixture of pre-assigned local answers can mimic quantum statistics. GHZ tells you that the conflict can be laid bare without averaging, making it impossible to dodge by saying maybe the sample was biased. It also sharpens contextuality. The meaning of each local answer depends on which complementary questions are being asked at the other sites, not because a spooky signal flies between them, but because the joint property you are measuring, those parities, is not built from independent, context-free parts. Quantum mechanics still respects the ban on faster-than-light messaging. Each lab's local stream of pluses and minuses is individually random, and no choice made elsewhere imprints a readable mark on a single lab's data. What changes is what you count as a legitimate global description. The GHZ state forces you to abandon the comforting image of 3 beads each with a hidden pair of yes-no stickers. Instead, you adopt a picture where some truths belong to the trio as a whole, and trying to ascribe them to the parts produces nonsense. That may sound like a philosopher's flourish, but it is the exact mental move you make in engineering when you stop pretending that a system's performance can be decomposed into independent components and you start designing for constraints that only make sense collectively. If you want to carry one last piece of intuition, make it this. GHZ states are the purest example of how quantum theory turns either or into both and at the level of relations rather than outcomes. Each run still yields definite local answers, no blurry half-clicks, but the relations among those answers for different patterns of questions cannot be carved into pre-existing local chunks. They arise from a phase-coordinated structure that the trio shares. You do not need heavy algebra to respect that. You need a new habit. When a phenomenon gives you joint facts that are sharper than its parts, believe the joint facts and resist the urge to retrofit them into private ledgers. That habit, born in the tidy logic of GHZ, will serve you wherever deeply connected systems live. Whether you are debugging a quantum chip, designing a protocol for 3 honest but mistrustful partners, or simply retraining your intuition to accept that sometimes reality writes its rules not on the individuals, but on the chorus. Pusey, Barrett, Rudolph versus epistemic dreams. You've probably comforted yourself with a simple picture of uncertainty, that the quantum state is like a weather forecast or a sealed envelope, a tidy way of packaging your incomplete knowledge about what's really there. And the Pusey-Barrett-Rudolph theorem walks in like a calm auditor and says, if that were all the wave function was, then certain perfectly ordinary experiments you can do with independently prepared systems would contradict the very predictions you trust, which is the heart of PBR versus Pusey epistemic dreams. A careful argument that pushes you to decide whether the quantum state is merely a catalogue of information or a piece of reality's furniture. To feel the force of the result without symbols, use an envelope analogy. Suppose a lab can prepare one of several colors of a single particle's state, and your epistemic hope is that different colors sometimes refer to overlapping collections of underlying physical situations, like 2 different weather forecasts that are both compatible with the same hidden sky. If that overlap exists, then there are real physical micro-stories that could have produced either color of state equally well. From this viewpoint, ESI is only your description, not the thing itself. PBR asks you to do something banal: prepare 2 particles in separate rooms with no coordination beyond following the same recipe, then bring them together and perform a joint test designed to tell certain pairs of colors apart in one shot. Their key assumption, called preparation independence, simply says that if you build 2 systems independently, the pair's underlying physical condition is just the product of the 2 singles conditions, the way 2 sealed envelopes from different addresses don't secretly contain matching letters unless the sender's coordinated. Under that assumption, if different colors of psi correspond to overlapping hidden stories, then some joint hidden stories will make the pair compatible with more than one combination of colors at once. PBR show you can design a conclusive exclusion measurement that, according to quantum mechanics, never clicks for one particular color combination, yet your overlapping story model insists that sometimes it must click. In plainer language, if psi were only ignorance about a deeper goings-on, and if independent preparations really were independent at the microscopic level, then there are experiments you could do that would produce outcomes quantum theory forbids. Because those outcomes are never seen, the overlap picture is in trouble. The escape route is obvious but costly. Deny preparation independence, allow the 2 envelopes, prepared in different rooms, to share hidden, prearranged correlations every time, or deny that measurement outcomes depend only on the local hidden story of the system being probed. Either move saves the epistemic dream, but at a price that many find steeper than simply admitting that psi itself is ontic, a real descriptor of the world, rather than a mere summary of what you know. This is not scholastic hair-splitting. It hits a nerve because the knowledge-only view of PSI had an intuitive champion in toy models that reproduce a surprising amount of quantum behavior by treating states as probability distributions over hidden variables that indeed overlap. Those models are educational and beautiful, but they deliberately stop short of full quantum predictions. PBR identifies where full predictions slam the door. The theorem's logic leans on the existence of anti-distinguishable sets of states, families, of preparations for which there exists a test that is guaranteed to rule out one member in a single shot. If distinct PSIs shared hidden stories, some pair of independently prepared systems would, with non-zero chance, land in a joint hidden situation that your test is supposed to exclude with certainty, forcing a contradiction. The elegance of PBR is that it doesn't accuse you of naivete. It just shows that to keep PSI purely epistemic and keep quantum predictions intact, you must accept a world where every time two experimenters claim to prepare systems independently, the hidden variables behind the scenes collude in just the right way to avoid the exclusion. That collusion can be framed as deep, fine-tuned correlations baked into the universe's initial conditions, a superdeterministic flavor, as retrocausal influences that link future measurement choices to past hidden states, or as a denial that independent labs really exist except as stories told by coarse-grained observers. None of those are logical impossibilities, but each shifts the burden of explanation. Instead of PSI being a simple bookkeeping device, independence itself becomes a fragile illusion, or a principle you cannot rely on without caveats. If you're wondering whether nature has weighed in, experiments have tested PBR-inspired inequalities and state exclusion tasks with photons, trapped ions, and solid-state qubits. They cannot test preparation independence in the philosophical absolute, but they can push it hard by randomly choosing preparations in separated modules and then performing the joint measurement that quantum theory prescribes. The data line up with the quantum prediction that the excluded outcome never occurs within experimental error, which is exactly what you expect if distinct phecies are not quietly sharing hidden micro-realities. These tests don't settle metaphysics, but they do convert a debate that used to be traded in adjectives, knowledge-like versus real-like, into one traded in apparatus and counts. Related theorems reinforce the pressure from other angles. Arguments by Kolbeck and Renner show that if you keep a robust notion of free choice for measurement settings and demand no superluminal signaling, then in a precise sense, PSI must be in one-to-one contact with whatever deeper description you're trying to write, again pushing you away from a comfortably overlapping knowledge-only view. The cumulative effect is that the psi epistemic dream, taken at face value and with ordinary independence assumptions, struggles to breathe in the same room as the experiments we easily perform. But the story isn't accept psi as a Beeble or go home. Some interpretations change the grammar of what a state means to dodge the theorem without conspiracies. In agent-centered frameworks, the quantum state is explicitly a user's betting book rather than a claim about hidden furniture. That move declines to posit an underlying variable space at all, so PBR's overlap of distributions premise never gets off the ground. In strictly operational views, preparation independence is not a microphysical axiom, but an experimental guideline, and the theory's job is to map lab procedures to outcome statistics, not to certify whether a deeper joint microstate exists. And there are realist but non-classical models that accept SI as part of the ontology, while still insisting that other non-psi variables play roles in dynamics or probabilities. PBR leaves those untouched. What PBR does is narrow the menu. If you want psi to be only about ignorance, and you want to keep the straightforward independence of labs, and you want to recover ordinary quantum predictions, the triangle doesn't close. You must relax at least one corner, and the theorem tells you exactly which ones are on the table. What should you carry out of this, besides a trophy, from a foundational debate? First, a crisper sense of what independence buys you. The mundane assumption that two systems prepared apart don't share hidden whispers is not a background neutral. It powers learnability and modularity in science. If you trade it away to keep an epistemic sigh, you owe yourself a new account of how experiments in separate rooms ever tell a coherent story together. Second, a healthier respect for the wave function's role as a coordinate on reality, not merely a gloss on ignorance, an attitude that quietly guides how we build quantum technology. In tomography, control, and error correction, engineers already act as if the state is a manipulable element of the world. PBR gives philosophical cover for that practice. Third, a reminder that no-go theorems are not cages. They are maps of the terrain. PBR didn't end interpretation. It told you which trails circle back on themselves and which cut cleanly forward. And the closing reflection is gentle. Perhaps your instinct to treat uncertainty as ignorance was never wrong. It just fits better in the classical rooms of the house. In the quantum rooms, the furniture includes ESI itself. You can still reason, still predict, still learn. You just accept that sometimes the truest description of what is there isn't a secret card behind the state, but the state you already write down. Maxwell's demon, Landauer's bill at the door. You meet a tiny gatekeeper in your imagination, a meticulous bouncer stationed at a microscopic door between two gas chambers, who watches molecules whiz by and, with perfect timing, opens the door for fast ones going left and slow ones going right. And in your mind's eye, the temperature difference grows, a pressure gap appears, and it seems as if the second law of thermodynamics has been outwitted by clever bookkeeping. But Maxwell's demon is not a magician so much as an accountant, and the debt it racks up arrives, inevitably, as Landauer's bill at the door. Begin with the promise the demon dangles before you. If you can sort particles by speed without spending energy, you could extract work from a single heat bath, running a tiny engine forever without fuel, which would be a tidy perpetual motion machine of the second kind. The resolution is not to sabotage the demon's reflexes or to shout measurement costs energy as a mantra, because measurement, in principle, can be done reversibly, but to notice that the demon must remember what it has learned to make its next move, and in a finite memory, remembering means erasing old bits to make room for new ones. An erasure is the place where physics presents the invoice. Landauer's principle, articulated in 1961 and refined by Bennett and others, is simple to say and profound to implement. Any logically irreversible operation, like resetting a memory register to 0, regardless of whether it held a 0 or a 1, must dump at least kBTLN2 kBTLN2 of heat into the environment per bit erased, a tiny but real amount, about 3 trillionths of a trillionth of a joule at room temperature, because squeezing two possible logical states into one physical state is a one-way compression that raises the entropy you push into the surroundings. In the demon story, the trapdoor itself can be light, the measurements can be delicate, but the creature's notebook eventually fills, and clearing that notebook, returning it to a standard blank slate so the next cycle can start, heats the world by exactly the amount needed to restore the second law's dignity. No free lunch, just a temporarily hidden tab. To see the stakes without equations, shrink the gas to a single molecule in a box with a movable piston. The Szilard engine. If you could learn which side the molecule is on and then let it push the piston out, you would harvest work from your knowledge, repeat this many times, and you'd build a pump powered by information. But the cycle only closes if you put your memory back to its ready state, and doing so costs at least as much free energy as you gained, unless you push that cost elsewhere. Either way, the net ledger respects the law. This is not armchair philosophy. Experiments using colloidal particles trapped by light or single electron boxes in nanoscale circuits have literally measured the heat of erasure, watching energy dump into a thermal bath as a 1-bit memory is reset, and the numbers hover right around Landauer's bound when the process is done as gently as engineering allows. Other groups have run information engines, measuring a particle's position and then feeding back to extract work, only to find that when you include the information used, counted in bits, the generalized second law is intact. Work out Humspaw's free energy drop plus k const bt k bt times the information you gained. What you learn, slowly and then all at once, is that information is physical, not because thoughts have weight, but because representing alternatives takes up distinct, thermally, jostled arrangements of matter, and crushing alternatives into one outcome has a thermodynamic price. The nuance that keeps the story honest is that not every act of learning burns energy. What burns is forgetting in a way that discards which alternative was true. You can, in principle, compute and even measure in a logically reversible style, choreographing steps so that no information is thrown away. And heat production can, in theory, be made arbitrarily small by going arbitrarily slowly. But as soon as you insist on a tidy reset to zero or compress data to free up storage, Landauer's bill lands on your desk, scaled by the number of bits you crush. That is why reversible logic, think Fredkin-Toffoli gates, is not a mere curiosity. It is a map toward designs where heat is tied to intentional irreversibility, not to computation itself, and why clever data compression can lower the minimal cost of clearing memory. If you can encode your records into fewer bits without loss, you erase fewer bits and pay a smaller unavoidable fee. The Demon Tale also clarifies everyday technology in a way you can feel in your palm. Why does your phone grow warm when you clear caches or stream video? Why do data centers guzzle megawatts and exhale heat? Not because today's engineers are sloppy, but because large-scale information handling is a festival of erasures, buffers flushed, logs rolled, registers reset, and each crushed bit, multiplied by astronomical counts and sped up to billions of times per second, becomes real heat that fans and cooling towers must carry away. As devices shrink toward molecular scales, those tiny per-bit costs stop being rounding errors. They shape how fast and how densely we can compute without boiling our chips, and they motivate error-correcting codes and architectures that steer unavoidable erasures into components designed to shed heat cleanly. The principle even guides biology and sensing. Molecular machines like enzymes and motors move in an environment where measuring and deciding are inseparable from thermal noise, and the efficiency they can achieve is bounded by the same bookkeeping that binds the demon. In measurement, the sharpest detectors flirt with limits, where each discriminated bit of outcome drags a minimal entropic price somewhere in the apparatus. None of this invites despair or mysticism. It invites better questions. If you want cooler, more efficient computing, target the logical irreversibilities in your algorithms and hardware, slow the steps that must be irreversible, and recycle information where you can. If you want to harvest work from fluctuations, build feedback that is precise and frugal, but keep a clean account of the memories you reset. And if you need a litmus test for perpetual motion claims in the age of clever nanotech, ask where the erasures happen and where the heat goes. If the answers are vague, the demon is hiding the bill off the books. The human echo is gentle. In thought as in thermodynamics, remembering can be cheap, but deliberate forgetting, folding many possible stories into a single clean page, has a cost you pay somewhere, sometime. Maxwell's demon isn't a cautionary monster, it is your inner auditor, reminding you that clarity and order are precious precisely because they are purchased, and that every tidy reset of a device, a dataset, or even a decision owes a small, honest warmth back to the world. Zeno and anti-Zeno. Freeze or speed up change. You've been told since childhood that a watched pot never boils. And in quantum physics, that homespun line becomes a controlled experiment with two endings. One where the water really does stall, and another where your very act of watching turns on the flame. And learning which happens and why is the story of the Zeno and anti-Zeno effects, the art of freezing or accelerating change by how and how often you look. Start gently with a single unstable system. Like an atom in its excited state, that would normally shed a photon and relax. In everyday courses, you're shown a tidy exponential curve for its chance to survive. But the curve's first breaths are different. At extremely short times, the survival doesn't fall linearly. It bends as a gentle quadratic, meaning the very earliest drift away from the initial state is slower than the later textbook rate. That early quirk is all Zeno needs if you perform sharp, frequent interrogations that ask, "Are you still excited?" And you space those questions closer than the timescale on which the curve straightens into an exponential. Each interrogation resets the clock back to the gentle bend regime. Stack enough resets and the atom barely moves. This is the quantum Zeno effect in its cleanest form. Repeated projective checks inhibit the transition, not because consciousness glares at the atom, but because each check is a physical interaction that refreshes the state and suppresses the coherent buildup needed for decay. The picture has a continuous cousin. Even without staccato on-off measurements, strong continuous coupling to a probe can dephase the would-be transition so relentlessly that the system is dynamically decoupled from the pathways that would carry it away. In both versions, watching means making the alternatives distinguishable in a way that cuts off the flow from one to the other. Now pivot to the apparent paradox. The same act of monitoring can also speed up decay. The key lies in a trade you already know from sound and color. The shorter the time slice of a signal, the broader its spread of frequencies. Frequent, aggressive probing chops the system's energy line into a broader band. In the Zeno regime, that broadening misses the environmental frequencies that accept the transition, so nothing happens. But if the surroundings, vacuum modes, lattice vibrations, tunneling continua, offer a dense set of acceptor states near that broadened band, your probing increases the overlap with those acceptors and the transition accelerates. That is the anti-Zeno effect. Measure often enough, but not too often, or couple in a way that widens the system's spectral line to match the bath, and you shorten the lifetime rather than extend it. Which side you land on depends on two clocks and one profile. The interval between your looks, the environment's memory time, how quickly it forgets a disturbance, and the spectral density of states the system can jump into. Look faster than the environment can mix away your disturbance, and you get Zeno. Look on a slower cadence that still disturbs, and in the wrong landscape, you get anti-Zeno. This is why there's no single recipe. You must match the rhythm of your interrogation to the rhythms of the world around the system. The facts live in hardware, not poetry. Trapped ion teams first showed that a rapid series of "Are you excited?" pulses can stall an otherwise reliable transition. Cold atom experiments in optical lattices tuned the rate of gentle kicks to either halt tunneling between wells or boost it. Solid-state groups watching spins in diamond or superconducting circuits have used continuous readout to lock a state in place and then, by detuning the probe, flip the setup into anti-Zeno and watch decay speed up. Across platforms, the diagnostics all rhyme. Increase your interrogation frequency and the transition probability per unit. Time first dips, then rises. Vary the bath spectrum and the crossover point shifts. Make your measurements too weak to distinguish the alternatives, and both effects fade because the system keeps its coherence. Notice what this story is not claiming. It's not that looking with eyes does anything special, only interactions that can, in principle, create a record count. It's not that the second law or causality wobble, the energy budget balances, and no signal outruns light. What changes is the rate at which a system exchanges energy and information with its surroundings because you have altered the available pathways. And it's not that Zeno lasts forever. If your probes are imperfect, or if the environment's memory is short, or if technical noise adds random phase, the freeze eventually thaws. What you should keep is the testable criterion. Zeno thrives in the quadratic window, with measurements faster than the bath's correlation time. Anti-Zeno appears when measurements or dephasing are frequent enough to broaden levels, but not so fast that they force the system to restart from zero every time, and when the broadened band finds more to couple to than the narrow one did. The uses are as down-to-earth as they are counterintuitive. In quantum control, Zeno is the conceptual backbone of dynamical decoupling. Rapid, structured interactions keep a qubit from leaking by repeatedly interrupting the mechanisms that would scramble it. When you need to move information quickly, controlled anti-Zeno can, in principle, act like a catalyst, increasing coupling where you want it, for example, speeding population transfer in a designed photonic environment. In chemistry, shaping the radiation field or solvent spectrum around a reactive complex can push it toward the Zeno side, stabilizing a fragile intermediate, or toward anti-Zeno, nudging it over a barrier, an idea that blends spectroscopy with control. In metrology, guarding a sensor against inadvertent anti-Zeno is part of keeping drift honest. If your readout broadens the line into regions of higher loss, you'll watch sensitivity erode and blame the sample. Redesign the probe to keep it in Zeno's shadow and the same device suddenly holds still. And in quantum networks, understanding when continuous monitoring of a node freezes desired dynamics versus accelerates loss tells you whether to watch a fragile link or to shield it, aligning supervision with the bath's memory rather than fighting it blindly. Each application hides the same calculation in different clothes. What does your interrogation do to the overlap between the system's broadened transition band and the environment's menu? Cut the overlap and you get stillness. Expand it and you get hurry. There are subtleties worth savoring because they keep your understanding honest. First, Zeno with weak measurements is real. You don't need to slam the system. A rapid stream of gentle, noisy peaks can suppress change if the information they could, in principle, carry about the transition builds up faster than the transition itself. Second, negative result monitoring counts. Even a detector that would have clicked if the system had jumped but stays quiet can contribute to Zeno because the possibility of a recorded difference is enough to kill the coherence required for the jump. Third, contextuals. A probe that gives Zeno in one spectral landscape can produce anti-Zeno in another. Moving along a chip or changing the detuning of a cavity can flip the sign of your watchfulness. Finally, Zeno is not mere pausing. It can reshape pathways, suppress direct decay while opening a different, slower channel, or conversely, close a dark route and channel flow into a bright one. So the smartest use is not to freeze blindly, but to sculpt options. If you want a single sentence to hold the science together, take this. What we call watching changes a system's phase space of possibilities, and whether that change arrests motion or accelerates it is set by timescales and spectra, not by mystique. And there is an echo you can carry into ordinary life without cheating the physics. Some changes settle only if you stop poking them, while others need deliberate, regular attention to avoid drifting into waste. Either habit can be medicine or poison, depending on the context around it. The quantum story gives you a disciplined version of that wisdom. Ask quickly and cleanly, and a fragile state can hold. Ask with the wrong rhythm or in the wrong environment, and you speed the very loss you hope to avoid. Learning that cadence, when to pause, when to let flow, isn't just a lab craft. It is a way of thinking more gently about control itself, letting your questions shape change when they help, and stepping back when they harm, so that what must endure stays calm, and what must move, moves. Loschmidt's paradox and reversibility. Start with a picture you can feel in your hands. You scramble a deck, let the cards scatter into a mess, and watch order drain away. So obvious that you'd stake your common sense on it, then Johann. Loschmidt taps your shoulder and says, "Play the film backward." And suddenly the same microscopic rules that drove the scramble could, in principle, pull every card back into a perfect stack, which is the sting of Loschmidt's paradox. If the underlying equations are reversible, why does entropy march one way? The answer is not a loophole hidden in the forces, because at the microscopic level, the equations that move atoms are essentially time-symmetric. It is a story about assumptions and initial conditions that you and I smuggle into our descriptions. The moment we trade a handful of molecules for a gas, a single trajectory for a probability cloud. Boltzmann's celebrated H theorem, his route from reversible laws to an arrow of time, quietly inserts a clause called molecular chaos. The claim that just before collisions, the velocities of molecules are uncorrelated in a way that lets you multiply probabilities. That clause is physically reasonable for a gas expanding from a simple, unstructured start. But it is not invariant under time reversal. If you reverse every velocity after a stretch of ordinary evolution, the correlations run backward, become exquisitely tuned, and the same theorem would predict entropy decrease provided you kept the correlations instead of discarding them. Loschmidt's point is surgical. You cannot derive an arrow from symmetric laws without paying somewhere, in the assumptions about the past, or in the way you ignore correlations. Boltzmann's reply, sharpened by generations since, is that the payment is honest and precisely where it should be. First, the world we inhabit began in a special, low-entropy macrostate, a past hypothesis, not because the laws demand it, but because that's the boundary condition we were given. From such a beginning, typical microstates compatible with any coarse description overwhelmingly evolved toward macrostates that occupy larger volumes in phase space, so almost every forward trajectory increases entropy, while the time reverse, though allowed, is incredibly rare and fragile. Second, your everyday entropy is a coarse-grained statistic. You divide phase space into fat cells and report only which cell you're in, not your exact coordinates. Hamiltonian flow preserves the fine-grained volume by Liouville's theorem, but under coarse graining, the cloud of microstates gets filigreed and stretched until it spreads across many cells, and your limited description calls that spread higher entropy. Reverse the film, and you must reverse not only every speed, but also your information policy. You must refuse to coarse grain at the precise scale where the filigree remains legible. We never do, and the arrow appears. None of this denies the existence of exceptions. Poincaré recurrence assures you that an isolated, finite system will, after absurdly long times, return arbitrarily close to where it began. Fluctuation theorem tell you that in small systems watched over short intervals, you will sometimes see negative entropy production, and can even quantify how those rare, uphill blips fade as systems grow. These are not cracks in the second law, they are its refinements, telling you exactly how the improbable is priced, and why the average still leans one way. Nature has even offered laboratory parables that honor Loschmidt without surrendering to him. In a spin echo, you scramble the phases of many nuclear spins in a magnetic field. Entropy seems to rise as the collective signal dies. Then you flip the sign of the dephasing, and the chorus reforms. A macroscopic whisper of reversibility. In a Loschmidt echo for quantum systems, you try to rewind dynamics by inverting the Hamiltonian and measure how faithfully the original state returns, discovering that small imperfections grow at rates set by chaos, so echoes fade unless your control is exquisite. The message is consistent across scales. Reversibility is real in principle and delicate in practice. The arrow is not a brute force in the equations, but a statistical habit born of simple starts, typical evolution, and the way we summarize. If you want a cleaner mental ledger, separate three ideas that often get tangled. First, laws versus boundary conditions. The same symmetric rules can support many arrows. We live in one picked by a special beginning. Second, microstates versus macrostates. Nothing in mechanics forbids a scrambled deck from unshuffling, but the set of microstates that do it is a measure zero filigree compared to the dull, mixed C. Third, fine-grained truth versus useful truth. At perfect resolution, entropy is constant, but at the resolution where you and your instruments live, mixing looks like growth, and that looks like is not a weakness. It is the only truth you can act on. Holding those distinctions turns the paradox from a threat into a guide. It teaches you why simulations remain honest only if you respect correlations, why models of climate, plasmas, and crowds must declare their coarse graining up front, why scramblers and mixers in technology work without violating anything, and why every refrigerator, engine, and algorithm pays in waste whenever it throws away detail. And the closing human echo is quiet but firm. You cannot build meaning out of laws alone. You need beginnings and a habit of ignoring what doesn't matter. And that act of ignoring is creative and costly. Loschmidt asked you to imagine the world playing backward, so you would notice the choices hidden in how you watch it. Once you do, the one-way drift you feel in broken eggs, cooling coffee, and aging cities is no longer a puzzle to defeat, but a pattern to understand, manage, and, in rare, artfully planned moments, like an echo brought back from silence, briefly and beautifully reverse. Superdeterminism. Did freedom ever exist? You've been told that the strength of quantum weirdness rests on a modest freedom. That experimenters may choose what to measure without that choice being secretly choreographed by the very particles under test. And superdeterminism begins by denying that modesty, asking you to consider a universe where the settings of your switches and the hidden properties of the systems you probe share a deep common cause, so that the apparent violations of Bell's limits never force you to accept non-locality, because the inequalities assumed a kind of independence that on this view never existed. Start with the clean logic you can hold in your head. Bell's theorem says, no local model with pre-assigned outcomes can reproduce the correlations. Quantum mechanics predicts if three assumptions are kept: local causality, no faster than light influence, a single outcome per run, and measurement independence, the idea that the variables describing the pair of particles are statistically uncorrelated with the later choices of measurement settings. Superdeterminism keeps locality and single outcomes, and discards measurement independence, positing that the hidden variables and your button presses are already correlated, perhaps by conditions set in the distant past. So the data that look like non-local magic are, in this story, just well camouflaged common causes. You might protest that experimenters have bent over backward to randomize settings, flipping coins, sampling laser phase noise, even using photons from ancient quasars to pick angles. And yet a superdeterminist shrugs. If the correlations run all the way back to the universe's initial microstate, your cosmic dice are part of the same script. A model that is deterministic all the way down can tie today's choices and yesterday's hidden variables with a thread you cannot cut by any local randomizer. The challenge then is not logical possibility, but scientific plausibility. In causal language, dropping measurement independence means allowing a link from the choices nodes to the hidden variable node in the graph. But to match quantum predictions and preserve no superluminal signaling, those links must be tuned so that, despite the underlying coordination, each laboratory's local outcomes remain individually random and unexploitable for communication. That tightrope is what many critics call fine-tuning. If the correlations between settings and hidden variables were even slightly off the quantum prescription, you'd either break the observed statistics or open a back door to signaling. So a successful superdeterministic theory must provide a dynamical mechanism that makes the required tuning natural, not a list of coincidences declared just so. This is where the conversation leaves philosophy and asks for engineering. What would such a mechanism look like? One route imagines that the apparent randomness of settings is the surface of a vast deterministic substrate, cellular automaton, like dynamics or pilot, wave, style, kinematics, whose initial conditions, plus ordinary local evolution, seed long-range statistical patterns that happen to align settings with hidden variables exactly as needed. Another route attempts to show that typicality with respect to a special global measure on states guarantees the right correlations in almost all worlds consistent with our macroscopic history, much as the past hypothesis makes low entropy at the Big Bang typical for the arrow of time. Either way, the bar is high. Predictivity must be earned by deriving where quantum theory should fail. Because if a superdeterministic model simply reproduces all of quantum mechanics with no extra constraints, it adds metaphysical baggage without empirical payoff. So, how could you ever test a claim designed to dodge Bell tests? You change the question. First, you quantify how much measurement dependence is needed to simulate the observed violations. You can translate the needed conspiracy into a mutual information between settings and hidden variables. Then look for physical mechanisms that would imply side effects of exactly that dependence. Subtle biases in auxiliary data streams, correlations between nominally independent random sources or context, dependent noise that tracks setting generators across very different platforms. Second, you diversify the setting sources, not because cosmic photons force freedom back into the theory, but because varied mechanisms, human decisions, hardware noise, astronomical light, make any single common cause story work harder, and a real dynamical model would predict where dependence is strongest or weakest. Third, you push beyond Bell to regimes, where superdeterministic coordination is harder to hide. In contextuality tests that knit together many measurement bases, in sequential experiments where settings are chosen adaptively based on intermediate outcomes, or in device, independent randomness expansion, where any hidden link between early settings and later devices should leak as a detectable reduction in certified entropy. Fourth, you look for deviations from quantum statistics that a deterministic substrate might naturally produce, teeny failures of independence in multi-source interference, constraints on higher-order correlations in networks, or characteristic non-Markovian patterns in time. Series of outcomes that repeat across platforms. A useful superdeterministic theory wouldn't just wave at initial conditions. It would publish inequalities with slack, new bounds that quantum theory saturates, but that the theory predicts will be slightly under or over, shot in identifiable circumstances. Then the data can do what they always do. Keep the theories that missed least, retire the rest. Alongside these pragmatic moves, keep the conceptual distinctions tidy. Superdeterminism is not retrocausality. Nothing flows from future to past. It is a claim about common causes linking what you treat as free choices to what you measure. It is not the denial of agency in a moral sense. Physics already treats free choice operationally as statistical independence, not as a metaphysical verdict on your will. It does not invalidate scientific inference wholesale. If such correlations exist, they must be exquisitely structured, and science would simply expand its models to include them. Think of how we already treat confounders in epidemiology. The real cost sits with parsimony and explanatory depth, a world where any awkward correlation can be blamed on unobservable initial coordination risks, becoming untestable. Unless it also tells you where coordination breaks. That's why many researchers lean toward principles like information causality, no superluminal signaling, and independence of settings as the cleanest way to pick quantum theory out of a larger family. Drop independence, and you inherit the duty to supply a replacement principle strong enough to earn its keep. If this still feels like a threat to your everyday sense of, I could have done otherwise, take a breath and separate personal experience from statistical structure. In practice, you will keep designing experiments as if your choices are independent, because that assumption is operationally fertile. It lets you factor probabilities, design fair tests, and build devices whose security can be certified without peeking inside. If a future superdeterministic model arrives with honest, testable departures from quantum statistics, you will adjust. If none does, the freedom assumption remains the best tool we have. Not because it is sacred, but because it is useful and so far undefeated. And there is a small, humane echo here worth keeping. You do not need cosmic independence to act meaningfully. You need frameworks that make your actions predictively separable from the systems you study, so that learning can proceed. Superdeterminism, if it matures into a proper theory, will either respect that separability in practice and become a reinterpretation of familiar numbers, or it will predict where separability fails and become a better map. Until then, the right posture is neither panic nor romance but craft. Specify what dependence means. Propose mechanisms that generate it without fine-tuning. Write down discriminating tests and let data decide. Freedom, in the scientific sense, isn't a metaphysical crown. It's a working assumption that earns its place by surviving attempts to remove it. And the only honest way to ask whether it ever truly existed is to build the theory that tries to live without it, and see where it breaks. Contextuality paradoxes in simple setups. Pick up the simplest toys you can imagine. 5 yes, no questions arranged around a circle, or a tidy grid of 9 switches, and ask them in carefully chosen groups. And you'll meet a quiet revolution hiding in plain sight. Contextuality. The discovery that in the quantum world, the result you can sensibly ascribe to a property depends on the full set of other, compatible questions you simultaneously ask, so that trying to give every question a context, free pre-existing answer leads you into contradictions in setups so small and clean, they feel like riddles for children until they school you. Start with the 5 questions, known in the literature as the KCBS pentagon, but which you can hold as a playground rule. You may ask any 2 neighbors together, and in a non-contextual world, one where each question has a definite yes or no independent of what else you check. You cannot answer yes to more than 2 of the 5 without breaking the adjacency rule. That bound is just a compact way of saying you can't color the circle with too many yeses. If neighboring questions must never both be yes. Quantum mechanics. When you engineer 5 gentle, compatible tests on a single system, think of a spin pointed in 5 carefully chosen directions, lets you exceed that bound, not by issuing a forbidden pair of yeses in a single context, but by arranging the averages over many runs so that context by context, the pattern of yeses is more generous than any pre-assigned list of truth values allows. The key is that each pair you are allowed to ask together has its own internal harmony, and the system's responses are tuned to those harmonies. Try to stitch all the contexts into one global coloring, and the thread snaps. If you crave something even more tangible, turn to the Paris Fey Mermin, Magic Square, a 9-switch cartoon you can implement with polarized photons or trapped ions. The rules are simple to state without algebra. Each row of 3 switches is designed so that when you flip them together, the parity of their outcomes must be even. Each column is designed so that when you flip those 3, the parity must be odd, or vice versa, depending on convention. In actual experiments, the quantum device keeps both promises deterministically. Row-wise checks always give you even, column-wise always odd, but if you tried to assign each of the 9 switches a fixed value in advance, independent of which row or column you'd later choose, what non-contextual realism asks you to do, you'd be forced to predict an even number of total yeses by the row condition and an odd number by the column condition. An arithmetic impossibility with no appeal to statistics. The contradiction is surgical. The square proves that there is no single context-free ledger of switch values consistent with what you can jointly measure reality, at least at the scale of these observables, refuses to be summarized by a list that exists prior to and independent of the questions you actually pose together. This is not about tricking yourself with incompatible measurements. The tests within each row or column are chosen to be mutually compatible. And it is not about hidden signals between distant labs. It is a local tabletop exposure of a deeper rule. Joint facts need not decompose into independent parts. To keep your footing, notice what contextuality is and isn't. It is not randomness for randomness' sake. In the square and the pentagon, the relevant parities or averages are perfectly reproducible. It is not a loophole that better engineering will close. Cleaner hardware only sharpens the conflict with non-contextual assignments, and it is not an invitation to say, anything goes. Contexts are precise, which tests commute, which can be bundled, which parities are guaranteed. The moral is modest, but radical. The meanings of some outcomes are relational, tied to the measurement frame you build around them, and trying to promote them to universal properties. Detached from that frame creates logical knots you can see with 9 switches and 5 questions. Why should you care beyond a neat puzzle? Because contextuality is a resource you can spend. In quantum computing, the power to outrun classical simulators in a fault-tolerant way is now tied to contextuality. Circuits built only from operations that admit a non-contextual description, so-called free operations in certain models, can be efficiently mimicked by classical algorithms The advantage appears when you inject special states, often called magic, whose statistics are provably contextual with respect to the rest of the circuit. In plain terms, contextuality is to quantum computation what nonlinearity is to optics, the ingredient that lets you leave the easy regime. In sensing and communication, contextuality certifies that correlations you're exploiting cannot be reproduced by devices that merely shared randomness. That's the backbone of device. Independent guarantees where you distrust the inner workings of your black boxes and rely only on the logical impossibility of a non-contextual explanation for the patterns you see. It also trains your engineering intuition. If a design tacitly assumes that each component carries a context-free setting that downstream modules read, contextual experiments warn that at the quantum edge the interactions among compatible tests can create global constraints you must honor. Ignoring them leads to architectures that look consistent on paper, but cannot be realized without hemorrhaging performance or introducing noise that spoils the very parities you depend on. There are practical recipes, too, for witnessing contextuality without heavy math. Build the magic square with single photons polarizations and path degrees of freedom, or with 3 qubits on a superconducting chip. Calibrate so that within each row or column, your devices truly commute, no stray crosstalk, and record parities over many runs. The clean violation of any non-contextual model emerges as soon as you see the row and column promises hold together, or implement the pentagon with a single trapped ions spin and 5 laser defined bases arranged so that neighbors commute tally the average number of yes outcomes allowed by the experimental rules and watch it breach the classical cap. As you turn the knobs, introducing decoherence, misalignment, or deliberate context mixing, the magic fades in a controlled way, teaching you exactly which imperfections reintroduce a non-contextual explanation. That last point is not a footnote, it's a diagnostic. Contextuality is exquisitely sensitive to the right kind of noise, so monitoring it becomes a way to assess when your platform has slipped back into a regime a classical model could fake. There is also a philosophical dividend, more practical than it first appears. Contextuality is not a license to say that properties don't exist until you look. It says that the assignments you can consistently make depend on the web of compatible questions that define your look. In classical life, you already live with gentler cousins of this. A person's role depends on the group they are with. A city's speeds depends on the coordinate system you've chosen. The same object can be a seat in one plan, an obstacle in another. Quantum contextuality makes this dependence crisp and testable at the level of physical properties you once believed could be listed without reference to a frame. If you want a habit of mind to carry out of the lab, make it this. When you design a measurement, write down the entire context that gives your outcomes meaning. Resist the urge to paste results from incompatible frames into one ledger. And when your system's joint promises look impossible under a context, free view. Believe the promises and reconsider the view. In return, the world gives you tools, pentagons, and squares that act as litmus tests for whether you are operating in a truly quantum regime. Parity checks that double as gates for computation, and simple, tabletop paradoxes that, once learned, make you a better engineer of fragile truths. The closing comfort is gentle. Contextuality doesn't make reality fickle. It makes your questions honest. Ask with the right companions and the system will answer with parities and patterns no classical coloring can match. Force one answer to stand alone when it only lives in chorus, and you'll hear the discord that taught us, with just 9 switches and 5 neighboring queries, that the quantum world is not a list of facts waiting to be read, but a grammar in which facts and the sentences that hold them belong together. Spekkens' toy model. How far can classical go? Suppose I hand you a sealed token that could be in one of 4 hidden configurations. Picture a little square with 2 arrows, one pointing along X and one along Z's. Each arrow either left feign right or up fey down. And I impose a strict rule that you may never know both arrows at once. At best, you can learn one arrow exactly while the other must remain a coin flip. and every allowed state of knowledge is a fair mixture over two of the four possibilities. That simple, almost childlike constraint is the beating heart of Spekkens' toy model. And if you follow it faithfully, you will watch a surprising amount of quantum-looking behavior bloom from entirely classical pieces, which is why the model is such a sharp tool for asking, how far can classical go if I only limit knowledge? You start by adopting the knowledge balance principle. For a single toy bit, call it a toy bit, the true microscopic situation. The ontic state is one of four corners on your x-phase square. But any epistemic state, what you are allowed to claim, must be a uniform distribution over exactly two corners, knowing x wipes out z and vice versa. Measurements are just partitions of the square. Ask, what is x? And you group left, corners versus right. Corners ask, what is z? And you group top versus bottom, because the rule bans you from holding both arrows. Any sharp answer must be paid for by randomizing what you cannot know. That payment gives you, for free, a raft of phenomena, often taught as if they require complex amplitudes. Disturbance, learning X forces ignorance about Zen, a clean no-cloning theorem. If you can never pin down a full microstate, you cannot build a copier that reproduces all allowed epistemic states. And even state exclusion games, where the best you can do is probabilistic, because your ignorance is built in rather than tacked on as detector noise. Transformations in the toy world are simply permutations of the four corners that respect the legal partitions. Surprisingly, these permutations are rich enough to mimic interference, like effects at the level of your knowledge. Two-step procedures can undo each other in one context, while acting non-trivially in another. So, what you don't know can add and cancel in patterns that look suspiciously wave, like when you track only the allowed summaries. Build a two-toy-bit system, and the model goes further. You can prepare correlated epistemic states, where each toy bit by itself is maximally unknown, but the pair is constrained. If the first is left, the second is right. If the first is up, the second is down, and so on. So that joint measurements reveal tight relationships with no signal riding between the labs. With those shared constraints and a dash of classical communication, you can stage toy teleportation, relaying an epistemic state from one place to another without the intermediate token carrying it remote steering of what descriptions are sensible at a distance, mirroring the choreography of entanglement protocols without any spooky influence or complex vector spaces. All of this emerges from bookkeeping, not mysticism. Once you bake complementarity into what agents can jointly know, you must accept measurement disturbance, uncertainty trade-offs, and information. Theoretic limits that look and feel like their quantum counterparts. But the model's value is not only that it explains, it also refuses. And the refusals are where you learn what really sets quantum mechanics apart, because the toy rules are built from classical microstates with epistemic constraints. The model is local and non-contextual at the deep level. You can always imagine a global ledger assigning facts to every test, even if the agent is never allowed to read the whole ledger. As a result, the toy world cannot violate Bell inequalities and cannot reproduce the magic square or pentagon contradictions, where quantum outcomes resist any single context independent assignment. It also cannot realize universal quantum computation. You'll find analogues of stabilizer tricks and error detection, but the magic resources that fuel speed ups are missing because the allowed transformations never wander outside a class that clever classical algorithms can simulate. Even its teleportation and entanglement are pedagogical illusions in a precise sense. The correlations are entirely explainable by shared classical structure plus ignorance. There is no monogamy of entanglement beyond what ignorance itself enforces. No violations of causal inequalities. No indefinite order. Those ceilings are not embarrassments. They are diagnostics. They tell you that a huge slice of quantum phenomenology, the part that feels like learning, disturbs. Complementary questions exclude. Cloning fails. Knowledge can be carried without carriers. Can be traced to limits on simultaneous knowability. and needs no uniquely quantum substance. The truly non-classical edges live where contextuality, non-locality, and certain computational resources appear. And there, the toy model simply stops. That stopping point is a gift, because it lets you ask sharper, why questions? Why does quantum theory allow Bell violations, while the toy world does not? Because quantum states are not just summaries of ignorance over hidden classical states. They carry a phase structure that the toy's flat probability rectangles cannot encode, and that phase becomes operational when contexts change. Why does universal quantum computation require special magic states? Because only when you're allowed descriptions break out of the toy's tidy partitions, injecting contextual statistics relative to the rest of your gates. Does classical simulation stumble? Why is no cloning deeper in quantum theory than you don't know enough? Because in quantum mechanics, the very geometry of state space forbids a single map from making perfect copies, even when you do know the full state vector. As a teacher, the toy model is a lens you can pick up at will. Use it to show students that uncertainty is not a synonym for sloppiness. In the toy world, it is a principle that disciplines what counts as a legal claim. Use it to stage gentle versions of quantum protocols. Key distribution with disturbance detection, teleportation, like relays, error detection, so they can see which steps rely on secrecy and which rely on something irreducibly quantum. Use it as a null model in experiments. If your observed statistics are compatible with a Spekkens style explanation, you have not yet reached the parts of parameter space where contextuality or non-locality become necessary. When a tweak pushes you past any toy explanation, you can say with confidence that the data demand quantum structure, not just clever classical ignorance. The same discipline helps in engineering. If a proposed sensor, random number generator, or cryptographic primitive claims quantum advantage, ask whether a toy model simulator could account for its performance. If yes, your advantage may be more marketing than physics. If no, identify the ingredient: contextuality, non-local correlations, non-Gaussianity, that the toy forbids and your device must truly harness. And there is a philosophical dividend that is neither cynical nor credulous. The toy model narrows what we should ascribe to metaphysics. Much of what impressed you on first learning quantum theory, the ban on perfect copying, the jolt of measurement, the trade between incompatible questions, needn't force you to invoke consciousness or many worlds. They fall out of a tidy classical cartoon the moment you forbid agents from overspecifying reality. What remains after that pruning? The parts the toy cannot fake. A aware interpretation earns its keep. So how far can classical go? Farther than you probably thought, but not all the way, with nothing more exotic than coins hidden under cups, and a rule that you may never lift both at once. You can recover a map of the everyday quantum look that is strikingly accurate across single systems and some gentle multi-system games. Yet when you demand the strongest correlations across distance, the sharpest contradictions across compatible contexts, or the full arsenal of quantum computation, the map runs out. That boundary is your takeaway. It tells you that quantum theory is not merely classical physics plus fuzziness, nor is it mystery all the way down. It is a layered structure, a broad base of information, theoretic constraints that classical cartoons can mimic, capped by a thinner but decisive crest of phenomena that require the full quantum grammar of complex phases and context-dependent structure. Learn the base to avoid romanticizing the ordinary. Learn the crest to stop explaining away what cannot be explained away, and carry the model like a pocket mirror. Before you call something quantum, hold it up to Spekkens' rules and see how much of the reflection survives. Whatever remains invisible there is, where the truly non-classical light begins.